Hey everyone, welcome back to the channel. Tonight we're diving into one of the most extraordinary detective stories in the history of science picture, this 66 million years ago. On what seemed like an ordinary spring morning, the Earth experienced the most catastrophic day in its entire history. In a single moment, an event so violent and so complete that it would erase over 160 million years of evolutionary dominance. The day the dinosaurs vanished wasn't just another extinction event. It was the cosmic equivalent of hitting the reset button on life itself. Now, before we get started, take a moment to hit that subscribe button if you're genuinely curious about the mysteries of our planet's past. And let me know in the comments where you're watching from and what time it is for you right now. It's always fascinating to see who's joining us on these journeys through deep time. So grab your favorite beverage, maybe dim the lights a bit, and let's travel back to that fateful day when the Age of Giants came to a sudden and violent end. Because what happened 66 million years ago wasn't just about dinosaurs. It was about the moment our entire world changed forever. The story begins not on Earth, but in the cold, dark reaches of the outer solar system far beyond Jupiter's orbit, where temperatures hover near absolute zero and sunlight is nothing more than a distant glimmer. A massive chunk of rock and ice had been drifting through space for billions of years. This wasn't your typical asteroid. Recent breakthrough research has revealed something absolutely remarkable about this cosmic wanderer. It was what scientists call a carbonaceous chondrite, a rare type of space rock that contains materials from the very dawn of our solar system. Think about that for a moment. This asteroid carried within it the primordial building blocks that existed when our sun was just forming, when the planets were still coalescing from cosmic dust. It was like a time capsule from the birth of everything we know. But unlike the rocky debris that typically bombards Earth from the inner solar system, this visitor from the outer reaches was fundamentally different. It was porous, light, and packed with volatile compounds that would prove absolutely devastating upon impact. The journey from the outer solar system to Earth represents an extraordinary cosmic event in itself. Something perhaps the gravitational influence of Jupiter or a collision with another object had nudged this mountain-sized rock out of its stable orbit. Once set in motion toward the inner solar system, it began a journey that would take millions of years to complete. Traveling through the void at incredible speeds, it passed the gas giants, crossed the asteroid belt, and eventually found itself on a collision course with our blue planet. By the time this cosmic missile entered Earth's atmosphere, it had grown to truly staggering proportions. Picture Mount Everest hurtling through space at 15.5 miles per second. That's the scale we're talking about here. Between 6 and 9 miles in diameter, this carbonaceous chondrite carried the kinetic energy equivalent to 10,000 times the entire world's nuclear arsenal. The sheer physics of this impact would release more energy than 100 trillion tons of TNT, more than 1 billion times the power of the atomic bombs dropped on Hiroshima and Nagasaki combined. Now here's where the story gets even more fascinating. Scientists have been able to determine not just when this impact occurred, but the exact season. Through painstaking analysis of fossil fish found at a remarkable site in North Dakota called Tanis, researchers have pinpointed the timing with unprecedented precision. The asteroid struck in late spring, sometime in May or June, during the transition from spring to summer in the northern hemisphere. The evidence comes from growth rings in the bones of ancient sturgeon, preserved in sediments that formed on the very day of impact. This seasonal timing is crucial because it helps explain why the extinction was so severe. Many species were in their most vulnerable reproductive phases. Nesting birds, spawning fish, and young animals just emerging into the world would have been particularly susceptible to the catastrophic environmental changes that followed. The impact site itself tells a story of unimaginable violence. When this mountain-sized projectile slammed into what is now the Yucatan Peninsula in Mexico, it created the Chicxulub crater, a wound in the Earth's surface that measures 120 miles across and 19 miles deep. To put this in perspective, It's one of the largest impact structures on our planet, and the only one where the original crater structure remains intact and accessible to scientific study. But the crater formation was just the beginning. Within minutes of impact, both the asteroid and massive amounts of Earth's surface material were completely vaporized. The temperatures at ground zero exceeded those found on the surface of the Sun. Any living thing within hundreds of miles would have been incinerated instantly, their bodies literally boiling and bursting from the extreme heat. The violence of this event sent 25 trillion tons of molten debris screaming into the atmosphere at speeds exceeding 100,000 miles per hour. This is where the story becomes truly global. The vaporized material didn't just disappear. It was blasted high into the stratosphere and beyond, creating what would become a planet-wide catastrophe. Among this debris were countless tiny glass beads called impact spherules, formed when droplets of molten rock cooled and crystallized in the vacuum of space before falling back to Earth like a deadly hailstorm. The Tanis site in North Dakota, located over 2,000 miles from the impact crater, preserves an extraordinary snapshot of what happened during those first crucial hours. Here, paleontologists have discovered the remains of fish, mammals, insects, and plants that died within the first hour of the asteroid strike. These aren't creatures that succumbed to the long-term effects of climate change or starvation. These are organisms that were killed by the immediate, direct consequences of the impact itself. The evidence is written in the rocks with startling clarity. Fish fossils have been found with impact spherules lodged in their gills, proof that these tiny glass beads were falling from the sky even as these ancient creatures struggled to breathe. The spherules themselves carry the chemical signature of the Chicxulub impactor, some even containing fragments of the original asteroid. This direct physical connection between the impact site in Mexico and the fossil site in North Dakota provides unprecedented evidence for what happened on that catastrophic day. But it wasn't just the falling glass beads that made this day so deadly. The impact generated seismic waves of incredible power that raced across the Earth's surface at tremendous speed. These weren't ordinary earthquakes. The ground shaking was so violent that it caused massive geological disruption across entire continents. In North Dakota, these seismic waves arrived within 30 minutes of impact, causing the rivers and lakes to surge and churn in what geologists call a seiche, a standing wave phenomenon that can move massive volumes of water instantaneously. The fossil evidence from Tanis shows creatures buried alive by these sudden water surges, their bodies preserved in sediments that accumulated in a matter of hours, rather than the thousands of years typically required for fossil formation. It's like having a photograph of the moment the world ended for these ancient organisms. Meanwhile, across North America, any dinosaurs still alive would have experienced something beyond imagination. The sonic boom from the impact would have traveled northward at the speed of sound, reaching Montana approximately 3 hours after the initial strike. The sound itself would have been powerful enough to rupture eardrums and cause internal injuries to large animals. Combined with the violent ground shaking that preceded it, this acoustic assault would have left surviving creatures disoriented and vulnerable to what was coming next. As the day progressed, the real horror began to unfold. Those impact spherules, now falling across the entire planet, carried with them a staggering amount of kinetic energy. As they re-entered Earth's atmosphere from space, friction heated them to incandescent temperatures. The collective energy of all these falling particles was equivalent to placing a 1 megaton hydrogen bomb every 6 kilometers across the entire surface of the Earth. The result was a phenomenon that scientists describe as a global thermal pulse. For several hours following the impact, the entire Earth was bathed in intense infrared radiation from these ballistically re-entering particles. The friction of their passage through the atmosphere turned each tiny spherule into a blazing torch, dramatically heating the air and igniting vegetation across vast areas of the planet. Any creature not underground or underwater faced an impossible situation. The thermal radiation was so intense that it could ignite dry vegetation and cause severe burns to exposed skin. This explains why certain groups of animals survived while others perished. Creatures that could burrow underground, dive deep into water bodies, or find shelter in caves had a chance. Those caught in the open, including most large dinosaurs, faced a hellish landscape of fire and superheated air. The scale of the resulting wildfires was unlike anything in human experience or geological history. Based on the amount of soot found in rock layers from this time period, some scientists estimate that the entire terrestrial biosphere may have burned. Imagine fires burning simultaneously across every continent, pumping enormous quantities of smoke and ash into an already debris-laden atmosphere. These weren't ordinary forest fires that might burn for days or weeks. Evidence suggests that major conflagrations continued for months, fed by the vast amounts of dead and dying vegetation killed by the thermal pulse. The smoke and soot from these planetary-scale wildfires would play a crucial role in what came next, adding to the growing atmospheric burden of dust and debris that was already beginning to block out the sun. As night fell on that first day, any surviving creatures would have looked up at a sky unlike anything seen before or since. The normal patterns of stars and moon were obscured by a growing shroud of dust, ash, and vaporized rock. The Earth was beginning its descent into what scientists call an impact winter, a prolonged period of darkness and cold that would last for years. The immediate aftermath had set the stage for a cascade of environmental changes that would ultimately determine which species lived and which would join the dinosaurs in extinction. The day that began with a single cosmic impact had triggered a series of interconnected catastrophes that would reshape life on Earth in ways that are still visible today, 66 million years later. But this was only the beginning of the story. The real test of survival was yet to come. The first 24 hours following the impact marked the beginning of a planetary transformation so severe that it would fundamentally alter the trajectory of life on Earth. As the initial fires raged and the debris cloud continued to thicken, the mechanisms of mass extinction began to unfold with ruthless efficiency. The vaporized sulfur from the impact site played a particularly sinister role in the unfolding catastrophe. The Yucatan Peninsula, where the asteroid struck, was rich in sulfur, bearing rocks called evaporites. When the impact occurred, these sulfur-rich minerals were completely vaporized and injected into the stratosphere. What made this especially devastating was the transformation that occurred next. The vaporized sulfur combined with water vapor in the upper atmosphere to form sulfuric acid aerosols, microscopic droplets that would remain suspended for years. These sulfuric acid particles were incredibly effective at reflecting sunlight back into space, far more so than the dust and debris from the impact itself. While dust particles settle out of the atmosphere relatively quickly, sulfur aerosols can persist in the stratosphere for years, creating a persistent veil that blocks solar radiation from reaching Earth's surface. This sulfur component may have been the most crucial factor in triggering the prolonged impact winter that followed. Within days of the impact, the combined effects of dust, soot, and sulfur aerosols had created a shroud so thick that photosynthesis ground to a halt across the planet. Recent climate models suggest that this period of darkness persisted for nearly 2 years in some regions. The temperature drop was severe, and sustained sea surface temperatures plummeted by as much as 13 degrees Fahrenheit in some areas, and freezing conditions likely lasted for at least 3 years. The collapse of photosynthesis triggered a domino effect throughout Earth's ecosystems that was both swift and merciless. Without sunlight, plants began dying within weeks. The first to succumb were the smaller, fast-growing species that depended on continuous photosynthesis for survival. Larger trees and shrubs with substantial energy reserves lasted longer, but even they eventually succumbed to the prolonged darkness. As plant life withered and died, the herbivorous dinosaurs faced an impossible situation. These massive creatures required enormous quantities of vegetation to sustain their metabolism. Within weeks of the impact, food became increasingly scarce. The smaller herbivores, with lower energy requirements, had a slight advantage, but even they struggled to find enough sustenance in a world where green plants were rapidly disappearing. The carnivorous dinosaurs initially had a temporary reprieve. The abundance of dead and dying animals provided a short-term food source, but this advantage was illusory. As the herbivore populations crashed, the predators found themselves without viable prey. The largest carnivores, with their massive energy requirements, were among the first to succumb. Their size, once an advantage in hunting, now became a liability in a world where calories were increasingly precious. Marine ecosystems faced their own catastrophic challenges. The impact had triggered massive tsunamis that swept across ocean basins, destroying coastal habitats and mixing surface waters with deeper oxygen-poor layers. The darkness that enveloped the planet also penetrated the oceans, shutting down marine photosynthesis and collapsing the base of oceanic food webs. Ocean chemistry itself began to change in dangerous ways. The massive amounts of carbon dioxide released by vaporized carbonate rocks, combined with acid rain from sulfur compounds, began to acidify the world's oceans. Marine organisms with calcium carbonate shells and skeletons were particularly vulnerable to these chemical changes. Many species of marine invertebrates, including numerous varieties of ammonites and marine reptiles, simply could not adapt quickly enough to survive. The selectivity of the extinction becomes clearer when we examine which creatures managed to survive this planetary catastrophe. Small size was clearly advantageous. Creatures that weighed less than 50 pounds had a much higher survival rate than their larger counterparts. This size advantage worked on multiple levels. Smaller animals required fewer calories to survive, could take advantage of scattered food sources that larger animals might overlook, and were better able to find shelter in burrows, caves, or dense vegetation. Behavioral adaptability proved equally crucial. Animals that could modify their diets, change their habitat preferences, or alter their activity patterns had better survival prospects. Many of the mammal species that survived were generalists, creatures that could eat a variety of foods and live in different environments. This flexibility allowed them to exploit new ecological niches as traditional food webs collapsed. The ability to find or create shelter was perhaps the most important survival trait of all. Creatures that could burrow underground, nest in tree cavities, or seek refuge in aquatic environments had protection from the thermal pulse, the falling debris, and the subsequent temperature extremes. This explains why so many burrowing mammals survived while surface-dwelling dinosaurs perished. Birds present one of the most fascinating cases of selective survival. Not all bird lineages made it through the extinction event. In fact, most of the diverse bird species that lived alongside dinosaurs went extinct. The survivors were primarily ground-dwelling and water-dwelling species that had access to seeds, aquatic invertebrates, and other food sources that remained available even after larger ecosystems collapsed. These surviving birds possessed several key advantages. Their ability to fly allowed them to search vast areas for scattered food sources. Their relatively small size meant lower energy requirements. Many could dive or swim, giving them access to aquatic food webs that were less severely impacted than terrestrial ones. Some species were also able to enter torpor or reduce their metabolic rate during the worst periods, a physiological adaptation that proved invaluable during the long months of environmental stress. The survival of certain turtle species offers additional insights into the extinction mechanism. More than 80% of turtle species managed to survive the boundary event. Their success likely stemmed from their ability to retreat into shells for protection, their generally slow metabolism that allowed them to survive on limited food, and their often aquatic lifestyle that provided some insulation from the worst environmental effects. Crocodilians also demonstrated remarkable resilience during this period. Their semi-aquatic lifestyle, ability to go long periods without food, and tolerance for environmental fluctuations helped them weather the crisis. These ancient predators had survived previous mass extinctions and possessed the physiological flexibility to endure dramatic environmental changes. The geographic pattern of survival also reveals important clues about the extinction mechanism. Species with large geographic ranges had better survival odds than those with limited distributions. This makes sense from an extinction perspective. If environmental conditions became uninhabitable in one region, widespread species had populations in other areas that might experience less severe effects. Interestingly, species restricted to high-latitude regions showed higher survival rates than those limited to tropical or subtropical areas. This pattern suggests that creatures already adapted to cooler, more variable climates were better prepared for the temperature drops and environmental instability that followed the impact. As months turned to years, the surviving species faced new challenges. The initial impact, winter gradually gave way to a period of global warming as carbon dioxide levels in the atmosphere increased dramatically. The vaporization of carbonate rocks during the impact had released enormous quantities of carbon dioxide, and the massive wildfires had added even more. Once the short-term cooling effects of dust and sulfur aerosols diminished, this greenhouse gas began to warm the planet significantly. This secondary warming phase created additional stress for species that had managed to survive the initial catastrophe. Organisms adapted to the cooler conditions of the impact winter now had to cope with rapidly rising temperatures. The combination of temperature swings, altered precipitation patterns, and continued ecosystem instability meant that recovery would be neither quick nor simple. The fossil record from the years immediately following the impact reveals a world in ecological chaos. Ecosystems that had remained stable for millions of years were completely restructured. Familiar predator-prey relationships disappeared. Plant communities were dominated by ferns and other species that could quickly colonize disturbed ground. Animal communities were simplified, with lower diversity and altered food web structures. Recovery was geographically variable and surprisingly slow, despite the abundance of vacant ecological niches. Evidence suggests that biodiversity recovery was more rapid in the southern hemisphere than in the northern hemisphere, possibly because the southern hemisphere experienced less severe environmental disruption during the initial impact and its immediate aftermath. The creatures that did survive found themselves in a world of unprecedented opportunity. With the dominant groups of the Mesozoic era eliminated, evolutionary radiation could proceed in entirely new directions. The small mammals that had lived in the shadows of dinosaurs for over 100 million years suddenly had access to ecological roles they had never before been able to exploit. This evolutionary explosion wouldn't happen immediately. The first few million years after the extinction were characterized by what paleontologists call the recovery fauna, a relatively impoverished collection of survivors gradually rebuilding their populations and beginning to diversify. But the stage was set for one of the most dramatic evolutionary radiations in Earth's history. The extinction had eliminated not just individual species, but entire ways of life that had dominated terrestrial ecosystems since the Triassic period. Large-bodied terrestrial herbivores and the predators that hunted them were gone. Aerial niches once occupied by pterosaurs were vacant. Marine ecosystems had been stripped of many of their most successful groups. Into this empty world, the survivors began to spread and adapt. The story of what happened next would be written by mammals, birds, and the other organisms that had managed to endure the most catastrophic day in Earth's history. But that transformation would take millions of years to unfold, and the world that eventually emerged would be fundamentally different from the one that existed before that spring day, 66 million years ago. The day the dinosaurs vanished had ended one chapter of Earth's story and begun another. The age of reptiles was over. The age of mammals was about to begin. The transformation of Earth's biosphere following the Chicxulub impact represents one of the most profound ecological reorganizations in the planet's history. As the survivors of that catastrophic spring day began to navigate their drastically altered world, the mechanisms of recovery and adaptation started to unfold across geological timescales that dwarf human comprehension. In the immediate aftermath of the extinction event, the planet's carbon cycle had been thrown into complete disarray. The massive release of carbon dioxide from vaporized limestone and the burning of organic matter had fundamentally altered atmospheric chemistry. While the initial cooling phase dominated the first few years after impact, the long-term effects of elevated carbon dioxide levels began to assert themselves as the dust and sulfur aerosols gradually settled out of the atmosphere. This transition from impact winter to greenhouse warming created a secondary wave of environmental stress that further tested the resilience of surviving species. The temperature swings were dramatic and rapid by geological standards. Within a few thousand years, global temperatures had shifted from the frigid conditions of the impact winter to levels significantly warmer than the pre-impact climate. This thermal whiplash eliminated additional species that had managed to survive the initial catastrophe but could not adapt to the rapidly changing conditions. The ocean systems, already severely disrupted by the impact, underwent fundamental restructuring during this recovery phase. The acidification that had begun immediately after the asteroid strike continued for hundreds of thousands of years as the planet's chemical systems slowly rebalanced. Marine food webs, stripped of many of their key species, were rebuilt from the bottom up by the organisms that had managed to survive in the deep ocean refugia, or had possessed the physiological flexibility to weather the chemical changes. Planktonic organisms, the microscopic foundation of marine ecosystems, showed particularly interesting patterns of recovery. Many of the calcium carbonate producing species that had dominated Cretaceous oceans were extinct, replaced by forms with different shell chemistries, or no shells at all. This shift had cascading effects throughout marine food webs, fundamentally altering the flow of energy and nutrients through oceanic systems. On land, the recovery process was equally dramatic, but followed different patterns depending on geographic location and local environmental conditions. The first plant communities to establish themselves in the post-impact world were dominated by ferns and other spore-producing species that could rapidly colonize disturbed ground. These pioneer communities created a fundamentally different landscape from the diverse flowering plant ecosystems that had characterized much of the late Cretaceous period. The absence of large herbivorous dinosaurs had immediate and far-reaching effects on plant community structure. Without these massive browsers and grazers, vegetation patterns began to shift in ways that would have been impossible during the preceding 160 million years of dinosaur dominance. Dense forests could develop without the constant pressure of large-scale herbivory, while open areas that had been maintained by dinosaur grazing began to change in character and composition. Insect communities, which had co-evolved closely with both dinosaurs and flowering plants throughout the Cretaceous, faced their own challenges during the recovery period. Many specialist species that had depended on specific plant or animal hosts went extinct along with their partners. The survivors were primarily generalist species that could adapt to new food sources and habitat conditions as ecosystems reorganized themselves. The small mammals that survived the extinction event found themselves in an ecological landscape unlike anything their lineages had experienced throughout their evolutionary history. For over 100 million years, mammals had been constrained to relatively small body sizes and nocturnal lifestyles by the dominance of dinosaurs. Suddenly, they had access to ecological roles and resources that had been unavailable to their ancestors. The initial mammalian recovery was slow and conservative. The earliest post-extinction mammal communities were dominated by small-bodied forms that differed little from their Cretaceous predecessors. But within a few million years, the first signs of the great mammalian radiation began to appear. Body sizes started to increase as some lineages began to exploit the vacant large herbivore niches left by the dinosaurs. This size increase wasn't uniform or immediate. Different mammalian lineages explored different evolutionary strategies as they adapted to their new world. Some remained small and retained the generalist feeding strategies that had served them well during the extinction event. Others began to specialize, developing new dietary preferences and habitat associations as plant communities stabilized and diversified. The surviving bird lineages underwent their own remarkable evolutionary transformation during this recovery period. The elimination of pterosaurs had opened aerial niches that birds could now exploit without competition from these flying reptiles. More importantly, the extinction of most large ground-dwelling dinosaurs provided opportunities for birds to radiate into terrestrial roles that had been unavailable throughout the Mesozoic era. Within 10 million years of the extinction event, some bird lineages had evolved to large body sizes and had begun to occupy predatory roles in terrestrial ecosystems. These early giant birds filled some of the ecological functions that had been performed by theropod dinosaurs, demonstrating the rapid pace at which evolution can proceed when ecological opportunities become available. The geographic patterns of recovery reveal fascinating insights into how life responds to global catastrophes. Regions that had experienced less severe immediate effects from the impact showed faster rates of ecological recovery and evolutionary innovation. Areas closer to the impact site, or regions that had been particularly affected by the environmental disruption, took longer to develop stable, diverse ecosystems. High-latitude regions, which had shown better survival rates during the extinction event itself, also demonstrated more rapid recovery patterns. The species that had survived in these areas were already adapted to environmental variability and cooler conditions, giving them advantages as they began to expand their ranges and diversify during the recovery period. The southern hemisphere showed particularly rapid rates of ecosystem recovery compared to the northern hemisphere. This pattern likely reflects both the distance from the impact site and the different seasonal timing of the extinction event. While it was late spring in the northern hemisphere when the asteroid struck, it was late autumn in the southern hemisphere, meaning that many organisms were already in dormant or less vulnerable stages of their life cycles. Ocean recovery followed different timelines depending on depth and distance from continental margins. Deep ocean environments, which had been partially buffered from the immediate effects of the impact, served as refugia for many marine lineages. These deep water communities provided the seed populations for the eventual recolonization of shallow marine environments as conditions stabilized. The re-establishment of coral reef ecosystems was particularly slow and difficult. The combination of temperature fluctuations, ocean acidification, and disrupted nutrient cycles created conditions that were inhospitable to the complex symbiotic relationships that characterize healthy coral communities. It took millions of years for stable reef ecosystems to redevelop, and when they did, they were dominated by different coral groups than had thrived during the Cretaceous. As the recovery progressed, entirely new types of ecosystems began to emerge that had no direct analogues in the pre-extinction world. The absence of large dinosaurs allowed for the development of plant community structures that would have been impossible under the browsing pressure of sauropods and the trampling effects of massive ornithopod herds. Dense, multi-canopy forests developed in some regions, while in others, open grassland ecosystems began to emerge for the first time in Earth's history. The evolution of grasses and grassland ecosystems represents one of the most significant ecological innovations of the post-extinction world. While grasses existed during the Cretaceous, they were relatively minor components of plant communities. In the post-impact world, these rapidly growing, highly productive plants found new opportunities to expand and diversify, eventually creating entirely new types of terrestrial ecosystems. The development of grasslands had profound effects on soil chemistry, water cycles, and fire regimes. These ecosystems supported different types of herbivore communities than the forest-dominated landscapes that had characterized much of the Mesozoic era. The coevolution of grasses and grazing mammals would become one of the defining features of Cenozoic terrestrial ecology. Climate patterns during the recovery period were highly variable and influenced by the complex interactions between atmospheric chemistry, ocean circulation, and the changing patterns of vegetation cover. The initial greenhouse warming that followed the impact winter was followed by a series of smaller-scale climate fluctuations as Earth's systems gradually rebalanced themselves. These climate variations provided additional selective pressures that shaped the evolutionary trajectories of recovering lineages. Species that could tolerate environmental variability had advantages over those that required stable conditions. This premium on flexibility and adaptability influenced the types of organisms that thrive during the recovery period and set the stage for the evolutionary patterns that would characterize the Cenozoic era. The fossil record from this recovery period reveals a world in constant flux, with ecosystems assembling and disassembling as species ranges shifted. New evolutionary innovations appeared, and environmental conditions continued to change. The stable, mature ecosystems that would eventually characterize the Middle and Late Cenozoic were still millions of years in the future. Understanding this recovery process provides crucial insights into how life responds to global catastrophes and how new evolutionary possibilities emerge from ecological devastation. The day the dinosaurs vanished had not only ended one chapter of Earth's story, but had also set in motion the processes that would write all the chapters that followed, including the one that would eventually lead to the emergence of our own species tens of millions of years later. The legacy of that catastrophic spring day continues to shape our planet today, influencing everything from the structure of modern ecosystems to the evolutionary relationships among living organisms. Every mammal alive today, including humans, owes its existence to the small, adaptable creatures that managed to survive the most catastrophic 24 hours in Earth's history and the remarkable recovery that followed. The evolutionary radiation that followed the extinction event represents one of the most spectacular examples of adaptive diversification in the history of life. As the survivors of that catastrophic day spread into vacant ecological niches, they began a process of evolutionary experimentation that would fundamentally reshape the biological landscape of our planet. The mammalian lineages that emerged from the post-extinction recovery displayed remarkable creativity in their evolutionary solutions to survival and reproduction. Within the first 10 million years following the impact, mammals had begun to explore body sizes and ecological roles that would have been unimaginable during the Age of Dinosaurs. Some lineages remained small and retained the nocturnal, insectivorous lifestyles that had characterized most Cretaceous mammals, but others began bold evolutionary experiments. The first large-bodied mammals appeared relatively quickly in geological terms, though their initial forays into gigantism were tentative and experimental. These early large mammals were unlike anything that had existed before, combining features from different mammalian lineages in ways that reflected the evolutionary uncertainty of a world still finding its biological equilibrium. Dental evolution provides some of the most fascinating insights into how mammals adapted to their new world. The diversity of tooth shapes and feeding strategies that evolved during the early Paleocene period reveals the range of food sources that became available after the extinction. Some lineages developed high-crowned teeth suitable for processing tough plant material, while others evolved specialized carnivorous dentition for exploiting the expanding populations of smaller mammals. The development of different locomotory strategies among early mammals reflects the diverse habitats and ecological opportunities that became available. Some lineages remained primarily terrestrial, developing more efficient running gaits as open habitats expanded. Others began to explore arboreal lifestyles as forest ecosystems recovered and diversified. A few even began the evolutionary journey toward aquatic specialization, taking advantage of marine and freshwater environments that were still recovering from the extinction event. Brain evolution accelerated dramatically during this period, with many mammalian lineages showing increased cranial capacity and more complex brain structures compared to their Cretaceous ancestors. This neurological expansion likely reflected the cognitive demands of navigating rapidly changing environments and exploiting new ecological opportunities that required behavioral flexibility and learning. The surviving bird lineages underwent equally dramatic evolutionary changes during the recovery period. The absence of pterosaurs had opened aerial niches that birds could exploit without competition, leading to rapid diversification in body size, flight capabilities, and feeding strategies. Some bird lineages became specialized for long-distance flight, developing the physiological adaptations necessary for crossing the expanding ocean basins and colonizing isolated landmasses. Other bird groups explored terrestrial lifestyles that had been impossible while large theropod dinosaurs dominated land ecosystems. These ground-dwelling birds evolved powerful legs for running, some reaching impressive body sizes that allowed them to become apex predators in early Paleocene ecosystems. Their success demonstrates how quickly evolution can fill vacant ecological roles when environmental opportunities arise. The evolution of flight capabilities among birds during this period shows remarkable innovation. Different lineages developed specialized wing shapes and flight styles adapted for particular ecological niches. Some evolved for high-speed pursuit of prey, while others developed hovering abilities for accessing nectar sources as flowering plants recovered and diversified. Plant communities during the recovery period underwent their own remarkable transformation, driven both by changing climate conditions and by the absence of large herbivorous dinosaurs. Without the browsing pressure of sauropods and the trampling effects of massive ornithopod herds, vegetation structure began to change in fundamental ways that had cascading effects throughout terrestrial ecosystems. The diversification of flowering plants accelerated during the early Paleocene, with many lineages developing new reproductive strategies, dispersal mechanisms, and defensive compounds. The coevolution between plants and their animal pollinators took on new dimensions as both groups adapted to post-extinction conditions and explored novel ecological relationships. Tree communities showed particularly dramatic changes in structure and composition. Without large dinosaurs to knock down trees and create clearings, forest ecosystems could develop more complex canopy structures than had been possible during the Mesozoic era. This architectural complexity provided new habitat types for the diversifying mammal and bird communities, creating three-dimensional ecosystems with unprecedented ecological diversity. The evolution of fruit production and seed dispersal strategies among plants reflects the changing composition of animal communities during the recovery period. Many plant lineages developed relationships with surviving mammals and birds, creating mutualistic partnerships that benefited both groups and contributed to the stability of recovering ecosystems. Soil ecosystems underwent fundamental restructuring during the recovery period as decomposer communities adapted to changed plant inputs and altered environmental conditions. The breakdown of organic matter proceeded differently in post-extinction soils, affecting nutrient cycling patterns and influencing the types of plant communities that could establish themselves in different regions. Fungal communities played crucial roles in ecosystem recovery, forming new symbiotic relationships with plant roots and helping to restore soil fertility in areas that had been devastated by the environmental catastrophe. The diversity and abundance of mycorrhizal fungi increased dramatically during the early Paleocene, reflecting their importance in supporting plant community recovery. Aquatic ecosystems showed their own patterns of recovery and diversification during this period. Freshwater environments, which had been severely disrupted by the acid rain and temperature fluctuations following the impact, gradually developed new food web structures as surviving species adapted to changed chemical conditions and new predator-prey relationships. The recovery of marine ecosystems proceeded at different rates in different ocean basins, influenced by factors such as water depth, proximity to continental margins, and local circulation patterns. Deep ocean communities, which had served as refugia during the worst phases of the extinction event, provided the source populations for recolonizing shallow marine environments as conditions improved. The evolution of new shell chemistries among marine invertebrates reflects the changed ocean chemistry that persisted for hundreds of thousands of years. After the impact, many lineages developed shells composed of different minerals or adopted entirely shell-less lifestyles as adaptations to the acidified marine environment. Coral reef recovery was particularly slow and challenging, requiring millions of years for stable communities to redevelop. When they did emerge, these new reef ecosystems were dominated by coral groups that had been relatively minor components of Cretaceous reefs, demonstrating how environmental catastrophes can completely restructure ecological hierarchies. The geographic expansion of surviving lineages during the recovery period created new biogeographic patterns that would influence evolution for millions of years to come. Continental positions were different from today, and ocean circulation patterns were still adjusting to the environmental changes triggered by the impact event. Island biogeography played an increasingly important role as sea levels fluctuated during the climate instability that characterized the early Paleocene period. Isolated populations on islands and continents evolved in different directions, creating the geographic diversity that would become characteristic of Cenozoic biogeography. The establishment of migration routes and corridors between different regions allowed for genetic exchange between populations and facilitated the spread of successful evolutionary innovations. These movement patterns helped to speed ecosystem recovery by allowing recolonization of areas that had been severely affected by the extinction event. Climate variability during the recovery period provided ongoing selective pressures that continue to shape the evolutionary trajectories of all major groups of organisms. The species that thrived were those that could tolerate environmental uncertainty and take advantage of rapidly changing conditions. The development of new climate feedback mechanisms involving interactions between vegetation, soil systems, and atmospheric chemistry began to stabilize global environmental conditions. These feedbacks would eventually lead to the more predictable climate patterns that characterize the Middle and Late Paleocene period. Ocean current patterns, disrupted by the environmental changes following the impact, gradually reorganized themselves as continental positions continued to shift and as marine ecosystems recovered. These changing circulation patterns influenced regional climate conditions and created new opportunities for marine organism dispersal and evolution. The fossil record from this recovery period reveals ecosystems in constant transition, with species compositions changing rapidly as environmental conditions fluctuated and as evolutionary innovations spread through populations. The mature, stable ecosystems that would eventually characterize the later Cenozoic era were still forming through this dynamic process of ecological assembly and disassembly. Understanding these recovery patterns provides crucial insights into the resilience of life and the creative potential of evolutionary processes when faced with catastrophic environmental change. The day the dinosaurs vanished had triggered not just destruction, but also unprecedented opportunities for evolutionary innovation and ecological reorganization. The legacy of that spring day, 66 million years ago, extends far beyond the extinction of dinosaurs. It fundamentally reset the evolutionary trajectory of life on Earth, creating the conditions that would eventually lead to the rise of grasslands, the diversification of mammals, the evolution of modern bird communities, and ultimately, the emergence of the lineages that would give rise to our own species. Every aspect of the modern biological world bears the imprint of that catastrophic day and the remarkable recovery that followed. From the structure of contemporary ecosystems to the evolutionary relationships among living organisms, the influence of the Chicxulub impact continues to shape our planet today, 66 million years after that mountain-sized asteroid transformed the history of life on Earth, The intricate web of cause and effect that emerged from that catastrophic spring day reveals the extraordinary interconnectedness of Earth's biological and geological systems. As we piece together the evidence from rock layers, fossil deposits, and chemical signatures scattered across the globe, a picture emerges of a planet undergoing the most rapid and comprehensive transformation in its 4.5 billion year history. The chemical fingerprints left behind by the Chicxulub impact tell a story that extends far beyond the immediate destruction. When researchers analysed ruthenium isotopes in 66-million-year-old rock samples from Denmark, Italy and Spain, they discovered something remarkable. The metal signatures matched exactly with those found in carbonaceous chondrite meteorites, providing definitive proof of the asteroid's identity and origin. This chemical detective work represents one of the most sophisticated forensic investigations ever conducted using evidence that has been preserved in Earth's crust for tens of millions of years. The ruthenium analysis revealed that within the last 500 million years, almost exclusively fragments from inner solar system asteroids have struck our planet. The Chicxulub impactor was extraordinary precisely because it came from so far away, carrying with it materials and properties that made its effects uniquely devastating. The porosity and composition of carbonaceous chondrites react completely differently from ordinary rocky asteroids during impact events. These outer solar system visitors are much more fragile and volatile rich, meaning they disintegrate more completely upon impact and release far greater quantities of vapor and debris into the atmosphere. This fundamental difference in asteroid type helps explain why the Chicxulub impact was so much more catastrophic than other large impacts throughout Earth's history. Understanding these material properties has profound implications for planetary defense strategies today. If another carbonaceous chondrite were to threaten Earth, our response would need to account for its unique characteristics. Unlike the rocky asteroids that typically approach our planet from the inner solar system, these outer solar system visitors require different deflection techniques and timing considerations. The seasonal timing of the impact continues to reveal new insights into the extinction patterns that followed. Spring in the northern hemisphere meant that many species were in their most vulnerable reproductive phases when the catastrophe struck. Nesting birds had eggs and young that were completely exposed to the thermal pulse. Marine organisms were in spawning cycles that left them unable to seek deeper water. Refugia, flowering plants, were investing energy in reproduction rather than building the reserves that might have helped them survive the coming darkness. This timing factor helps explain some of the puzzling aspects of the extinction record. Why did certain bird lineages survive while others perished? The answer may lie in their nesting behaviors and reproductive timing. Ground nesting species that were actively breeding in May and June would have been far more vulnerable than cavity nesting species, or those that nested later in the season. The Tanis site continues to yield extraordinary insights into the precise sequence of events during those first crucial hours. Recent analysis of plant fossils from the site shows that leaves and flowers were buried while still fresh, providing a snapshot of the vegetation that existed at the moment of impact. These plant remains carry pollen grains that confirm the late spring timing and reveal details about the ecosystem that existed in the final moments before the catastrophe. Amber deposits at Tanis have preserved insects with remarkable fidelity, including specimens that appear to have been killed while actively foraging or mating. These tiny time capsules provide intimate details about the behavior and ecology of organisms that lived through the most catastrophic day in Earth's history. Some insects have been found with impact spherules embedded in their bodies, direct physical evidence of the glass bead hailstorm that rained down from space. The preservation of soft tissues at Tanis defies conventional understanding of fossilization processes. Normally, the formation of fossils requires thousands or millions of years of gradual burial and mineralization. At Tanis, the rapid burial caused by seismic waves and water surges created conditions that preserved delicate structures like fish gills, skin impressions, and even cellular details that provide unprecedented insights into the physiology of extinction. Victims' pollen analysis from Tanis sediments reveals the immediate impact on plant communities. The normal diversity of pollen types that would be expected from a healthy late Cretaceous ecosystem disappears abruptly at the impact layer, replaced by a simplified assemblage dominated by fern spores. This fern spike is a classic signature of ecological devastation found at extinction boundaries worldwide, indicating the collapse of complex plant communities and their replacement by pioneer species. The geochemistry of Tanis sediments preserves evidence of the extreme environmental conditions that followed the impact. Elevated levels of iridium, osmium, and other platinum group elements provide chemical proof of the extraterrestrial origin of the catastrophe. These elements are rare in Earth's crust, but common in asteroids, making them reliable markers of impact events in the geological record. Analysis of carbon isotope ratios in Tanis fossils reveals the disruption of photosynthesis that occurred immediately after the impact. The normal patterns of carbon uptake by plants and marine organisms were completely disrupted, creating isotopic signatures that can still be detected in fossils today. This chemical evidence confirms that the collapse of primary productivity began within hours of the asteroid strike. The magnetic properties of impact spherules found at Tanis provide insights into the extreme temperatures and pressures generated by the collision. These tiny glass beads preserve magnetic orientations that formed when they cooled in Earth's magnetic field after being blasted into space. The magnetic signatures confirm that the spherules reached temperatures exceeding 2,000 degrees Celsius during their formation. Microscopic analysis of the spherules reveals their complex internal structure, with some containing unmelted fragments of the original asteroid. These inclusions provide direct samples of the impactor itself, allowing researchers to study the exact composition of the object that ended the Age of Dinosaurs. The chemical signatures match those of carbonaceous chondrites collected from space by meteorite hunters, confirming the asteroid's outer solar system origin. The shockwave patterns preserved in Tanis sediments reveal details about the propagation of seismic energy across the North American continent. The alternating layers of sediment show the rhythmic back and forth motion of water caused by the passage of seismic waves. These geological records allow scientists to calculate the exact timing and intensity of ground shaking at specific distances from the impact site. Recent discoveries at Tanis include the remains of a pterosaur wing and fragments of dinosaur skin, representing some of the youngest non-avian dinosaur fossils ever found. These specimens died on the very day of the impact, making them witnesses to the final moments of the Mesozoic era. Their preservation provides direct evidence that large reptiles were still thriving right up until the moment of the catastrophe. The study of coprolites, fossilized dung from Tanis, reveals what these ancient animals were eating in their final hours. The preserved stomach contents and waste products show that normal feeding behaviors were occurring right up until the moment of impact. This evidence contradicts theories that dinosaurs were already in decline before the asteroid strike, instead supporting the idea that the extinction was sudden and unexpected. Fossil feathers found in Tanis sediments preserve details about the coloration and structure of bird plumage from the end of the Cretaceous period. These microscopic structures, called melanosomes, can reveal information about the colors and patterns of ancient birds, providing insights into their behavior and ecology during the final days of the dinosaur era. The discovery of mammal burrows at Tanis shows how some creatures sought shelter during the catastrophe. These tunnels, filled with the same impact debris found in surface sediments, demonstrate that even underground refugia were not completely safe from the environmental chaos that followed the asteroid strike. However, the burrows also show that some mammals survived the initial catastrophe by seeking underground shelter. Fish fossils from Tanis preserve evidence of the immediate effects of falling impact spherules on aquatic ecosystems. Spherules lodged in gill rakers show that these glass beads clogged the breathing apparatus of fish, causing suffocation even for creatures that lived underwater. The spherules found in fish gills carry the same chemical signature as the Chicxulub crater, providing definitive proof that these animals died as a direct result of the asteroid impact. The sedimentary layers at Tanis record multiple pulses of deposition. suggesting that the environmental chaos continued for hours, or even days, after the initial impact. Each layer represents a different phase of the catastrophe, from the initial seismic waves through the spheral bombardment to the final settling of fine debris from the atmosphere. Paleomagnetic analysis of Tanis sediments confirms the rapid rate of deposition by showing that all the impact-related layers were deposited while Earth's magnetic field maintained the same orientation. This magnetic evidence proves that the entire sequence formed within a matter of hours or days, not the thousands of years that would normally be required for such thick sedimentary deposits. The preservation of tree rings in fossilized wood from Tanis provides insights into the growth conditions that existed immediately before the impact. These annual growth rings show that trees were growing normally right up until the catastrophe, with no indication of environmental stress or declining conditions. This evidence further supports the sudden nature of the extinction event. Chemical analysis of fossilized tree resin, or amber, from Tanis has revealed trapped gas bubbles that preserve samples of the atmosphere from 66 million years ago. These ancient air pockets provide direct measurements of atmospheric composition just before the impact, offering baseline data for understanding how the asteroid strike changed Earth's atmospheric chemistry. The discovery of flowering plant fossils at Tanis includes some of the earliest known examples of certain modern plant families. These specimens show that the diversity of flowering plants was reaching new heights just before the extinction event, making their subsequent collapse all the more dramatic. The plant fossils preserve pollen still attached to anthers, indicating that reproduction was actively occurring when the catastrophe struck. Fungal spores found in Tanis sediments reveal the role that decomposer organisms played in the immediate aftermath of the impact. The abundance and diversity of fungal remains suggest that these organisms quickly colonized the massive amounts of dead organic matter created by the extinction event, beginning the long process of breaking down and recycling the biological debris. The isotopic composition of water molecules trapped in Tanis minerals provides evidence of the hydrological disruption caused by the impact. Changes in the ratios of oxygen isotopes indicate that normal water cycle processes were severely disrupted, with implications for precipitation patterns and freshwater availability in the aftermath of the catastrophe. Analysis of microscopic crystals formed during the impact reveals the extreme pressures generated by the collision. These shocked minerals, including forms of quartz and feldspar that only form under intense pressure, provide direct physical evidence of the violent forces unleashed when the asteroid struck Earth. The crystal structures preserve a record of pressures exceeding those found deep within the Earth's mantle. The Tanis site represents just one window into the global catastrophe that unfolded 66 million years ago. Similar deposits are being discovered at sites around the world, each adding new pieces to our understanding of how the extinction event unfolded in different geographic regions and environmental settings. Recent discoveries in Antarctica have revealed impact debris layers in sediments that were deposited in polar marine environments during the extinction event. These Southern Hemisphere records show that the environmental effects of the Chicxulub impact were truly global, affecting ecosystems from the tropics to the poles. Deep ocean sediment cores contain their own record of the extinction event, preserved in the microscopic shells of marine organisms that lived and died in ancient seas. These marine records complement the terrestrial evidence from sites like Tanis, providing a comprehensive picture of how the catastrophe affected both land and sea ecosystems simultaneously. The integration of evidence from multiple sites and environments is revealing the true scope and complexity of the extinction event. What began as a single moment of cosmic violence set in motion a cascade of environmental changes that played out differently in different parts of the world, creating a complex mosaic of survival and extinction that shaped the future evolution of life on Earth. This growing body of evidence continues to refine our understanding of the most dramatic day in our planet's history, revealing new details about the moment when the Age of Dinosaurs ended and the Age of Mammals began. Each new discovery adds another piece to the puzzle of how life responds to catastrophic change and how new evolutionary possibilities emerge from global devastation. The global impact of that catastrophic day extends far beyond what any single fossil site can reveal. As researchers continue to uncover evidence from locations across the planet, a comprehensive picture emerges of environmental devastation that touched every corner of the Earth. From the Arctic tundra to tropical rainforests, from shallow coral reefs to the deepest ocean trenches, no ecosystem escaped the consequences of that spring morning 66 million years ago. Recent analysis of sediment cores from the Arctic Ocean has revealed impact debris layers that tell their own story of catastrophe. Even at these extreme northern latitudes, the geological record preserves clear evidence of the spherical bombardment and the environmental chaos that followed. These polar deposits show that the thermal pulse from falling debris was intense enough to ignite vegetation, even in regions that received limited direct sunlight during late spring. The preservation of organic matter in permafrost-like conditions has provided unprecedented insights into how Arctic ecosystems responded to the extinction event. Plant fossils from these high-latitude sites show a dramatic shift from diverse coniferous forests to simplified communities dominated by hardy shrubs and herbaceous plants. This vegetation change occurred within decades of the impact, demonstrating the speed with which ecosystems could collapse and reorganize Antarctic ice cores, though they don't extend back 66 million years, have provided valuable analogues for understanding how polar ice sheets might have responded to the dramatic climate swings that followed the impact. The rapid temperature fluctuations recorded in the younger ice cores reveal the potential for massive ice sheet instability during periods of extreme climate change, suggesting that sea level fluctuations may have added another layer of stress to already devastated coastal ecosystems. Deep ocean drilling projects have recovered sediment cores from locations that were thousands of miles from the Chicxulub impact site. Yet these marine records show clear evidence of the global reach of the catastrophe. The chemistry of microscopic shells preserved in these deep sea sediments reveals rapid changes in ocean temperature, acidity, and nutrient availability that began immediately after the impact. Planktonic foraminifera, microscopic marine organisms that float in ocean surface waters, show particularly dramatic patterns of extinction and recovery in these deep-sea records. These single-celled creatures form calcium carbonate shells that preserve detailed records of ocean chemistry and temperature. The extinction of many foraminiferal species at the impact boundary reflects the severe acidification and temperature changes that affected marine surface waters globally. The deep sea record also preserves evidence of the massive tsunamis that were generated by the impact. Layers of coarse sediment found thousands of miles from the impact site show the unmistakable signatures of high-energy water transport, indicating that enormous waves swept across ocean basins and penetrated far inland along continental margins. Continental shelf deposits from locations as distant as New Jersey and Denmark contain their own evidence of impact-related environmental disruption. These nearshore marine environments experienced some of the most severe effects of the extinction event, as they were simultaneously affected by tsunamis, temperature changes, acidification, and the massive influx of terrestrial debris washed into the oceans by the environmental chaos on land. The Brazos River section in Texas has provided crucial insights into how marine ecosystems in the Gulf of Mexico responded to the nearby Chicxulub impact. This site, located several hundred miles from the crater, preserves a detailed record of the immediate marine effects of the collision. The sediment layers show evidence of massive underwater landslides triggered by the impact, followed by the deposition of impact debris and the gradual recovery of marine life. Fossil evidence from the Brazos section reveals that marine ecosystems took much longer to recover than initially thought. While some organisms re-establish populations within thousands of years, the full restoration of marine biodiversity required hundreds of thousands of years. This prolonged recovery reflects the severity of the chemical and physical disruption to ocean systems. European sites have contributed their own unique perspectives on the extinction event. The Fish Clay Formation in Denmark preserves one of the most complete records of the extinction boundary available anywhere in the world. This thin layer of dark sediment contains high concentrations of impact debris mixed with the remains of marine organisms that died during the catastrophe analysis of the fish. Clay has revealed the presence of shocked minerals and impact spherules identical to those found at sites much closer to the Chicxulub crater. The global distribution of these impact markers confirms that debris from the collision was distributed worldwide within hours of the impact, creating a planet-wide environmental catastrophe. Fossil sites in Spain and France have provided additional evidence for the rapid environmental changes that followed the impact. These European localities show dramatic shifts in plant communities, with diverse late Cretaceous floras being replaced by simplified assemblages of hardy pioneer species. The speed of this vegetation change indicates that the environmental effects of the impact were both immediate and severe. The Hell Creek Formation in Montana and North Dakota has long been recognized as one of the most important sources of information about the end Cretaceous extinction. This geological unit preserves the final chapter of the Age of Dinosaurs in remarkable detail, documenting the diversity and abundance of life immediately before the catastrophe. Recent work in the Hell Creek Formation has revealed that dinosaur diversity remained high right up until the moment of extinction. Contrary to earlier suggestions that dinosaurs were already in decline, the fossil record shows that these magnificent creatures were thriving just before the asteroid impact. The sudden nature of their disappearance from the fossil record provides strong support for the catastrophic extinction hypothesis. The discovery of dinosaur remains within centimeters of the impact boundary layer in Hell Creek sediments demonstrates that non-avian dinosaurs survived until the very end of the Cretaceous period. These final dinosaur fossils include representatives of major groups like Triceratops, Tyrannosaurus, and various duck-billed dinosaurs, showing that the extinction eliminated entire lineages that had dominated terrestrial ecosystems for tens of millions of years. Mammal fossils from the Hell Creek Formation reveal a different pattern. While dinosaur diversity dropped to zero at the extinction boundary, mammalian diversity actually increased in the earliest Paleocene deposits immediately above the impact layer. This pattern reflects the rapid evolutionary radiation that began as soon as ecological opportunities became available to the surviving mammalian lineages. Plant fossils from Hell Creek provide detailed insights into how terrestrial vegetation responded to the environmental catastrophe. Pollen records show a dramatic decrease in diversity immediately after the impact, followed by a characteristic fern spike that indicates the colonization of devastated landscapes by pioneer plant species. The recovery of normal plant diversity took thousands of years, demonstrating the long-lasting effects of the extinction event on terrestrial ecosystems. Insect fossils from late Cretaceous and early Paleocene deposits reveal the cascading effects of plant community collapse on arthropod communities. Many specialist insects that had co-evolved with specific plant hosts went extinct along with their food plants. The survivors were primarily generalist species that could adapt to the simplified plant communities that characterize the immediate post-extinction world. The geographic scope of the extinction event becomes even more apparent when examining fossil sites from the southern hemisphere. Localities in Argentina, New Zealand, and Antarctica all show clear evidence of environmental disruption at the Cretaceous-Paleocene boundary, despite being thousands of miles from the impact site in Mexico. Southern Hemisphere sites are particularly important because they experience the impact during autumn rather than spring, providing insights into how seasonal timing affected extinction patterns. The evidence suggests that autumn timing may have provided some protection for certain species that were already entering dormant phases of their life cycles, when the catastrophe-struck marine reptile fossils from New Zealand reveal the extinction of magnificent creatures like mosasaurs and plesiosaurs that had ruled the oceans throughout the Cretaceous period. These marine giants disappeared as completely as their terrestrial dinosaur relatives, victims of the ocean acidification and food web collapse that followed the impact. The Salamanca Formation in Argentina preserves one of the most complete records of early mammalian recovery available from the southern hemisphere. This geological unit shows that mammalian evolution proceeded more rapidly in South America than in North America during the early Paleocene, possibly due to less severe environmental disruption in southern latitudes. Fossil leaf deposits from Patagonia document the recovery of plant communities in southern South America following the extinction event. These sites show that while initial plant community collapse was severe, recovery proceeded more quickly than in Northern Hemisphere locations. The reasons for this geographic difference in recovery rates remain an active area of research. Ocean drilling projects in the South Atlantic and Indian Oceans have revealed their own records of extinction and recovery in marine ecosystems far from the impact site. These Southern Ocean records show that while the initial environmental disruption was global, the patterns and timing of ecological recovery varied significantly between different ocean basins. The integration of evidence from all these widely distributed sites has revolutionized our understanding of mass extinction processes. Rather than being a simple, uniform catastrophe, the end Cretaceous extinction was a complex event that played out differently in different environments and geographic regions, creating a mosaic of survival and extinction that determined the future course of evolutionary history. Climate modeling studies have used this global network of geological evidence to reconstruct the environmental conditions that existed during and after the impact. These models show that the immediate effects of the collision, including the thermal pulse and initial cooling, were indeed global in scope. However, the longer-term recovery patterns were influenced by local factors such as latitude, altitude, proximity to ocean currents, and regional geology. The models reveal that equatorial regions experience the most severe and prolonged environmental disruption, while higher latitude areas recovered more quickly from the initial catastrophe. This pattern helps explain why so many surviving lineages appear to have originated from high-latitude refugia during the early stages of post-extinction recovery. Ocean circulation models show that the impact disrupted global patterns of heat transport and nutrient distribution for thousands of years after the collision. The reorganization of ocean currents affected regional climate patterns worldwide and influenced the geographic distribution of marine recovery communities. Atmospheric chemistry models demonstrate that the environmental effects of the impact were not limited to the immediate aftermath of the collision. The massive release of carbon dioxide from vaporized carbonate rocks created long-lasting changes in atmospheric composition that influenced global climate patterns for hundreds of thousands of years. These modeling studies, combined with the growing body of geological and paleontological evidence, have created the most comprehensive understanding ever achieved of a mass extinction event. The day the dinosaurs vanished was not simply a moment of destruction, but the beginning of a complex reorganization of Earth's entire biosphere that continues to influence the structure and function of modern ecosystems. The precision with which scientists can now reconstruct the events of that catastrophic day represents one of the greatest achievements of modern paleontology and geology. By combining evidence from dozens of sites around the world with sophisticated analytical techniques and computer modeling, researchers have created a detailed timeline of catastrophe and recovery that spans from the first seconds of impact through millions of years of evolutionary radiation. This understanding has profound implications that extend far beyond academic curiosity about ancient extinctions. The mechanisms revealed by studying the end Cretaceous catastrophe provide crucial insights into how modern ecosystems might respond to rapid environmental change. The patterns of survival and extinction that emerged from that ancient catastrophe offer important lessons about resilience, adaptation, and recovery that are increasingly relevant in our current era of rapid global change. The story of the day the dinosaurs vanished continues to unfold as new discoveries add detail and nuance to our understanding of this pivotal moment in Earth's history. Each new fossil site, each refined analytical technique, and each improved climate model contributes additional pieces to the puzzle of how life responds to catastrophic environmental change. What emerges from this ongoing research is a picture of life's remarkable resilience in the face of seemingly insurmountable challenges. The survivors of that spring day 66 million years ago faced a world that had been turned upside down. Yet they not only endured, but ultimately thrived, giving rise to the incredible diversity of life that surrounds us today. The legacy of that catastrophic morning continues to shape our planet in ways both obvious and subtle. Every mammal that walks the earth, every bird that takes flight, every flowering plant that blooms carries within its genes the evolutionary history that began with the survival and recovery of life after the most devastating day in our planet's history. Understanding this legacy provides perspective on both the fragility and the resilience of life on Earth. The extinction of the dinosaurs reminds us that even the most successful and dominant forms of life can be vulnerable to catastrophic change. Yet the remarkable recovery and diversification that followed demonstrates life's extraordinary capacity for renewal and innovation when faced with new opportunities and challenges. The day the dinosaurs vanished was simultaneously an ending and a beginning, a moment of destruction that created the conditions for unprecedented evolutionary creativity. In the ashes of that ancient catastrophe lay the seeds of the modern world, waiting for the opportunity to grow into the magnificent diversity of life that defines our planet today. This ancient story of catastrophe and recovery continues to inform our understanding of how life evolves and adapts in the face of environmental change. As we face our own era of rapid global transformation, the lessons learned from that distant spring day 66 million years ago provide valuable insights into the processes that shape the future of life on Earth. The investigation into the day the dinosaurs vanished represents one of science's greatest detective stories, a multidisciplinary effort that has revealed the intimate details of Earth's most dramatic transformation. Through the patient accumulation of evidence from around the globe, researchers have reconstructed not just the moment of impact, but the complex cascade of consequences that followed, creating our modern understanding of how worlds end and new worlds begin. The reconstruction of that catastrophic day has revealed layers of complexity that continue to astonish researchers around the world. As we delve deeper into the evidence, what emerges is not just a story of destruction, but a testament to the intricate connections that bind together all life on our planet. The ripple effects of that spring morning 66 million years ago created changes so profound that they fundamentally altered the evolutionary trajectory of every living thing on Earth. One of the most remarkable aspects of modern extinction research involves the sophisticated techniques scientists now use to peer back through deep time. Advanced mass spectrometry allows researchers to detect chemical signatures at the parts per billion level, revealing traces of the original impactor preserved in sediments worldwide. These microscopic fingerprints tell stories that would have been impossible to uncover just decades ago. The precision of these analytical methods has transformed our understanding of the extinction timeline. Rather than a gradual decline over thousands of years, the evidence now points to environmental collapse that occurred within decades of the initial impact. Geochemical analysis of boundary layer sediments shows that normal biological processes shut down almost immediately, with isotopic signatures indicating the cessation of photosynthesis across vast areas of the planet. Recent advances in paleomagnetic dating have refined the timing of events with unprecedented accuracy. The magnetic orientation of minerals in impact debris layers confirms that the entire catastrophic sequence unfolded while Earth's magnetic field maintained the same polarity. This magnetic evidence provides an independent confirmation that the massive environmental changes recorded in rock layers worldwide occurred within an extremely narrow time window. The development of new imaging techniques has revolutionized the study of fossilized soft tissues from extinction boundary sites. High-resolution scanning electron microscopy can now reveal cellular structures preserved in fossils, providing insights into the physiological state of organisms at the moment of death. These microscopic details paint a vivid picture of creatures caught in the midst of normal life activities when catastrophe struck. Synchrotron radiation analysis has enabled researchers to detect trace elements within fossil specimens at previously impossible levels of detail. This technology has revealed that many extinction victims show evidence of respiratory distress, consistent with atmospheric conditions that made breathing difficult for extended periods. The preservation of these physiological signatures provides direct evidence of the suffocating conditions that followed the impact. Advanced computer modeling has reached a level of sophistication that allows researchers to simulate the first hours and days after impact with remarkable precision. These models incorporate atmospheric physics, ocean dynamics, and biological processes to create comprehensive pictures of how environmental conditions changed in real time following the collision. The modeling reveals that the transition from normal conditions to global catastrophe occurred with breathtaking speed. Within 6 hours of impact, atmospheric temperatures had begun to spike due to the thermal radiation from falling debris. Within 12 hours, the first signs of photosynthetic shutdown were becoming apparent as atmospheric dust levels increased dramatically. By the end of the first day, global average temperatures had dropped by several degrees as the initial thermal pulse gave way to atmospheric darkening. Within a week, surface temperatures in many regions had fallen below freezing, even in tropical areas that had previously experienced year-round warmth. The speed of this environmental transformation exceeded anything in the geological record. Ocean circulation models show that marine systems experienced equally rapid disruption. The massive injection of fresh water from vaporized ocean water, combined with changes in atmospheric pressure and wind patterns, altered ocean currents within days of the impact. These circulation changes affected global heat distribution and marine nutrient cycles for thousands of years afterward. The chemical evolution of the atmosphere during the extinction event reveals a sequence of changes that would have been lethal to most forms of life. Initial vaporization of sulfur-bearing rocks created massive acid rain systems that persisted for months. The pH of precipitation dropped to levels that would dissolve calcium carbonate shells and damage plant tissues on contact. Atmospheric oxygen levels fluctuated dramatically as photosynthesis collapsed and massive wildfires consumed stored organic matter. Carbon monoxide concentrations spiked to toxic levels in many regions, adding another layer of stress to organisms already struggling with darkness, cold, and acid rain. The combination of atmospheric changes created conditions that would have been challenging for even the most adaptable species. Isotopic analysis of carbon compounds in boundary layer sediments reveals the complete disruption of the global carbon cycle. Normal patterns of carbon fixation by plants and marine organisms disappeared almost immediately, replaced by signatures indicating massive organic matter decomposition. This isotopic evidence confirms that primary productivity collapsed across both terrestrial and marine ecosystems simultaneously. The study of trace fossils, preserved evidence of ancient behavior, has provided unique insights into how surviving organisms adapted to post-impact conditions. Burrow systems from the immediate aftermath show changes in depth and complexity that suggest animals were seeking deeper refuge from surface conditions. These behavioral modifications represent some of the earliest adaptations to the changed world. Coprolite analysis from early recovery deposits reveals dramatic dietary shifts among surviving vertebrates. Herbivorous species began consuming previously ignored plant materials, while carnivores shifted to scavenging and new prey species. These dietary changes, preserved in fossilized stomach contents and waste products, document the collapse of established food webs and the emergence of new feeding relationships. Palynological studies of pollen and spore assemblages show that plant community recovery followed predictable ecological succession patterns, but at dramatically accelerated rates. Pioneer species, typical of disturbed environments, dominated for decades before more complex plant communities could re-establish themselves. The speed of these transitions reflects the severity of initial habitat destruction. The geographic patterns of recovery reveal fascinating insights into the role of refugia during mass extinction events. Certain regions, particularly those at high latitudes or in topographically complex areas, served as evolutionary safe havens where biodiversity persisted through the worst phases of environmental disruption. These refugial areas became the source populations for recolonization of devastated regions. Molecular clock studies of surviving lineages suggest that many modern groups underwent rapid evolutionary acceleration during the early recovery period. DNA analysis indicates that mutation rates increased significantly in the generations immediately following the extinction, possibly due to increased background radiation from cosmic rays penetrating the disrupted atmosphere. The evolution of detoxification mechanisms among surviving species represents one of the most remarkable adaptations to post-impact conditions. Many lineages developed enhanced abilities to process toxic compounds, cope with oxygen stress, and survive on degraded food sources. These physiological innovations became permanent features that continue to benefit their descendants. Today, biomineralization studies reveal how shell-producing organisms adapted to the acidified oceans that persisted for hundreds of thousands of years. After the impact, many species developed thicker shells or switched to different mineral compositions that were more resistant to dissolution in acidic water. These adaptations required fundamental changes in cellular metabolism and energy allocation. The recovery of reef ecosystems provides particularly detailed insights into community reassembly processes following mass extinction. Early Paleocene reef communities were dominated by organisms that had been minor components of Cretaceous reefs, demonstrating how ecological hierarchies can be completely restructured by environmental catastrophes. Trace element analysis of fossil shells reveals the changing chemistry of ancient oceans during the recovery period. Ratios of magnesium, strontium, and other elements document the gradual return to normal seawater chemistry as the effects of impact-related acidification slowly diminished. This chemical recovery took hundreds of thousands of years to complete. The study of growth lines in fossil shells and bones has revealed the seasonal and annual environmental variability that characterized the early recovery period. These growth patterns show that climate instability persisted for much longer than previously thought, with dramatic temperature and precipitation fluctuations continuing for millions of years after the initial impact. Paleoecological reconstruction of early recovery communities reveals ecosystems with simplified structure and altered energy flow patterns compared to pre-extinction communities. Food webs were shorter and less complex, reflecting the reduced species diversity and the dominance of generalist organisms that could exploit multiple resources. The geographic expansion of surviving lineages during recovery has been tracked through phylogeographic analysis of modern species. Distributions DNA studies reveal that many current biogeographic patterns originated during the post-extinction colonization of empty habitats, creating genetic signatures that persist today. Comparative studies of other mass extinction events have placed the end Cretaceous catastrophe in broader evolutionary context. While each extinction event has unique characteristics, the mechanisms of survival and recovery show remarkable consistency across different time periods, suggesting fundamental principles governing how life responds to catastrophic environmental change. The development of extinction selectivity patterns has revealed the traits that determined survival during the catastrophe. Small body size, broad geographic range, generalized diet, and flexible behavior emerge as key characteristics that enhance survival probability. These patterns provide insights into which species might be most vulnerable to current environmental changes. Recent discoveries of exceptionally preserved fossil sites from the recovery period have revolutionized understanding of post-extinction ecosystems. These Lagerstätten preserve complete organisms and ecological interactions, providing snapshots of life during the critical early phases of biosphere recovery. The integration of paleontological evidence with modern ecological theory has created predictive models for ecosystem recovery following environmental catastrophes. These models suggest that recovery patterns are highly dependent on the spatial scale and intensity of initial disturbance, with implications for understanding ecosystem resilience in the modern world. Experimental studies using living organisms have tested hypotheses about survival mechanisms during mass extinctions. Laboratory simulations of impact-related environmental stresses have confirmed many predictions about which physiological and behavioral traits would have enhanced survival during the extinction event. The emerging field of conservation paleobiology applies lessons from ancient extinctions to modern conservation challenges. Understanding how ecosystems recovered from past catastrophes provides insights into restoration strategies and helps identify which species and habitats are most vulnerable to current environmental threats. Climate proxy studies have reconstructed the detailed temperature and precipitation patterns that characterize the recovery period. These paleoclimate records reveal a complex sequence of environmental changes that varied significantly between regions and created the conditions for differential recovery rates across the planet. The study of evolutionary rates during recovery has shown that morphological evolution accelerated dramatically in many surviving lineages. Rapid changes in body size, feeding structures, and locomotory adaptations document the intense selective pressures that shaped post-extinction evolution. Stable isotope analysis of amino acids in fossil proteins has provided new insights into ancient food webs and metabolic processes. This cutting-edge technique can reveal dietary relationships and physiological states that were previously impossible to determine from fossil evidence alone. The discovery of impact-related nanodiamonds in boundary layer sediments has confirmed the extreme pressures and temperatures generated by the collision. These microscopic crystals form only under conditions far exceeding anything found naturally on Earth's surface, providing direct physical evidence of the violence of the impact event. Magnetostratigraphic studies have created high-resolution timelines for the extinction and recovery sequence. By correlating magnetic polarity patterns between widely separated fossil sites, researchers can synchronize events across different regions and create global timelines for the catastrophe and its aftermath. The analysis of shocked quartz grains in impact debris has revealed details about the mechanics of crater formation and debris dispersal. The crystallographic structure of these minerals preserves information about the pressure waves that propagated through Earth's crust during the collision, providing insights into the physics of large impact events. Biomarker studies of organic molecules preserved in ancient sediments have documented changes in microbial communities during the extinction and recovery. These molecular fossils reveal that bacterial and archaeal communities were also dramatically affected by the environmental changes, with cascading effects throughout the biosphere. The reconstruction of ancient food webs using network analysis has revealed the structural properties that made some ecosystems more resilient to extinction than others. Communities with greater connectivity and functional redundancy showed better survival rates and faster recovery times. Paleogeographic reconstructions have shown how continental positions and ocean configurations influence the geographic patterns of extinction and recovery. The arrangement of landmasses 66 million years ago created unique dispersal corridors and barriers that shaped the evolutionary responses of surviving lineages. The study of evolutionary developmental biology in fossil lineages has revealed how developmental constraints influence the directions of post-extinction evolution. Changes in gene expression patterns and developmental timing created the morphological innovations that characterize recovery faunas. Modern analog studies of ecosystems recovering from volcanic eruptions and other catastrophic disturbances have provided insights into the ecological processes that operated during the post-extinction recovery. These contemporary examples help validate models of ancient ecosystem dynamics. The integration of all these research approaches has created an unprecedented understanding of the most dramatic environmental catastrophe in Earth's recent history. The day the dinosaurs vanished was not simply a moment of destruction, but the catalyst for a complete reorganization of life on our planet. This reorganization established the evolutionary trajectories that would eventually lead to the modern world. The mammals that survived in small refugia would diversify into everything from tiny shrews to massive whales. The birds that endured the catastrophe would eventually fill the skies with thousands of species. The plants that colonized the devastated landscapes would evolve into the forests and grasslands that define terrestrial ecosystems today. The lessons learned from studying this ancient catastrophe extend far beyond academic interest in prehistoric events. Understanding how life responds to catastrophic environmental change provides crucial insights for predicting and managing the ecological consequences of current global changes. The resilience shown by life during that ancient catastrophe offers both warning and hope for the future. While the extinction demonstrates the vulnerability of even the most successful forms of life to environmental change, the remarkable recovery that followed shows life's extraordinary capacity for renewal and innovation when given the opportunity. The day the dinosaurs vanished marked the end of one chapter in Earth's biological history and the beginning of another. That spring morning, 66 million years ago, set in motion the evolutionary processes that would ultimately lead to the emergence of consciousness, intelligence, and the capacity to understand our own origins. Today, as we face our own era of rapid environmental change, the story of that ancient catastrophe and recovery provides both perspective and guidance. The mechanisms revealed by studying the end Cretaceous extinction help us understand how ecosystems respond to stress and how life finds ways to persist even in the face of seemingly impossible challenges. The ongoing research into this pivotal moment in Earth's history continues to reveal new details about the complex relationships between geological processes, climate systems, and biological evolution. Each new discovery adds depth to our understanding of how worlds end and new worlds begin. The day the dinosaurs vanished was truly the day that changed everything. A moment when the trajectory of life on Earth was permanently altered by forces beyond the control of any living creature. Yet from that moment of ultimate destruction emerged the conditions that would eventually give rise to the rich tapestry of life that surrounds us today. In the end, the story of that catastrophic day is not just about extinction and destruction, but about the remarkable ability of life to persist, adapt, and flourish, even in the aftermath of planetary catastrophe. It is a story that continues to unfold today as we discover new details about the most dramatic 24 hours in our planet's biological history. The legacy of that spring morning continues to shape our world in ways both profound and subtle, reminding us that we are all descendants of the survivors, inheritors of an evolutionary heritage forged in the crucible of the most catastrophic day in Earth's history. Understanding that legacy provides crucial insights into both our origins and our future as we navigate our own era of rapid global change. The profound implications of that catastrophic day extend far beyond the immediate destruction and recovery we've already explored. As scientists continue to piece together this ancient puzzle, what emerges is a story that fundamentally reshapes our understanding of how planetary systems respond to extreme disruption and how life itself adapts when faced with seemingly insurmountable challenges. The atmospheric chemistry changes that followed the impact created conditions unlike anything experienced in Earth's previous 4 billion years. The massive injection of water vapor from vaporized ocean water, combined with the release of chlorine and bromine compounds from evaporate deposits, triggered a complex series of chemical reactions in the upper atmosphere. These reactions destroyed the ozone layer over vast areas of the planet, allowing deadly ultraviolet radiation to penetrate to Earth's surface for the first time in geological history. The UV bombardment added yet another layer of stress to already devastated ecosystems. Plants that had survived the initial thermal pulse and the onset of impact winter now faced radiation levels that damaged their DNA and disrupted their cellular processes. This ultraviolet assault may explain why certain plant groups with more robust DNA repair mechanisms showed higher survival rates than their more vulnerable relatives. Marine ecosystems faced their own unique challenges during this period. The combination of temperature fluctuations, acidification, and increased UV penetration created a triple threat that eliminated many of the microscopic organisms that formed the base of ocean food webs, coccolithophores. Tiny marine algae that had been among the most abundant organisms in Cretaceous seas virtually disappeared from the fossil record at the extinction boundary. The collapse of these microscopic marine communities had cascading effects throughout oceanic ecosystems. Without the normal rain of organic matter from surface waters, deep-sea communities faced starvation on a scale unprecedented in marine history. Bottom-dwelling organisms that had thrived for millions of years suddenly found themselves in a world where food was scarce and unpredictable. The chemical signatures preserved in marine sediments reveal that ocean productivity remained severely depressed for hundreds of thousands of years after the impact. Normal patterns of nutrient cycling were disrupted by the elimination of key species, creating feedback loops that slowed the recovery of marine ecosystems far beyond what might have been expected from the initial disturbance alone. Terrestrial ecosystems underwent equally dramatic transformations as the environmental chaos continued. The loss of large herbivores created unprecedented changes in plant community dynamics. Without the browsing pressure of massive dinosaurs, certain plant species began to proliferate in ways that had been impossible throughout the Mesozoic era. The accumulation of dead plant matter, no longer consumed by herbivorous dinosaurs, altered soil chemistry and fire regimes across vast areas. Organic matter built up in unprecedented quantities, creating conditions that supported different types of decomposer communities and changing the fundamental biogeochemical cycles that had operated for millions of years. Insect communities, intimately connected to plant diversity and abundance, experienced their own waves of extinction and adaptation. Many specialist insects that had co-evolved with specific plant hosts found themselves without food sources as their partner plants disappeared. The survivors were predominantly generalist species that could switch between different plant hosts as availability changed. The disruption of pollination networks had profound effects on plant reproduction and evolution. Many flowering plants that had depended on specific insect pollinators were forced to develop new reproductive strategies. Some evolved to rely more heavily on wind pollination, while others developed broader pollinator relationships that provided greater security against future disruptions. Freshwater ecosystems present some of the most fascinating examples of selective survival during the extinction event. Many aquatic organisms showed remarkably high survival rates compared to their terrestrial counterparts. This pattern reflects the buffering capacity of water bodies against rapid temperature changes and their ability to provide refuge from the thermal pulse and falling debris. Rivers and lakes also served as corridors for the movement of surviving species during the recovery period. Aquatic plants and animals could disperse along water networks, allowing for more rapid recolonization of devastated areas. This connectivity may explain why freshwater communities recovered more quickly than many terrestrial ecosystems. The role of groundwater systems in supporting survival has only recently begun to be appreciated by researchers. Many organisms may have survived the worst phases of the extinction event by accessing underground water sources that remained relatively stable despite the chaos at the surface. Root systems of surviving plants show adaptations for deeper water access that may have developed during this critical period. Soil ecosystems underwent fundamental restructuring as the complex networks of roots, fungi, and bacteria that had characterized Cretaceous terrestrial environments were disrupted by plant community collapse. The mycorrhizal fungi that form symbiotic relationships with plant roots faced mass extinction as their plant partners disappeared, leading to major changes in soil nutrient cycling. The recovery of soil fertility became a limiting factor for plant community re-establishment in many regions. Areas where mycorrhizal networks had been completely destroyed took much longer to support diverse plant communities than regions where some fungal diversity had survived the catastrophe. Seed banks buried in soil provided crucial reservoirs of genetic diversity for plant community recovery. Many species that appeared to have gone extinct locally during the immediate aftermath of the impact were able to re-establish populations from seeds that had remained dormant in the soil for years or even decades after the catastrophe. The dispersal of seeds by surviving animals became critically important for ecosystem recovery. Birds, small mammals, and reptiles that had managed to survive the extinction event served as vectors for plant recolonization, carrying seeds across landscapes that had been stripped of vegetation. This animal-mediated dispersal helped to accelerate the recovery process in many regions. Wind patterns, altered by the changed atmospheric conditions following the impact, also played important roles in seed dispersal and ecosystem recovery. The disrupted circulation patterns created new pathways for long-distance seed transport, allowing some plant species to colonize areas far from their pre-extinction ranges. The evolution of dispersal mechanisms accelerated during the recovery period as plants adapted to the changed conditions. Many lineages developed more effective seed dispersal structures or formed new relationships with animal dispersers, adaptations that enhanced their ability to colonize disturbed habitats. Pollinator evolution proceeded in parallel with plant evolution during the recovery period. Surviving insects diversified rapidly to exploit the changing array of flowering plants, leading to the establishment of new pollination networks that differed substantially from those that had existed before the extinction. The coevolutionary dynamics between plants and their animal partners during the recovery period created some of the most important ecological relationships that characterize modern ecosystems. Many of the plant-animal interactions we see today can be traced back to partnerships that formed during the early phases of post-extinction recovery. Climate instability continued for millions of years after the initial impact, creating ongoing selective pressures that shaped the evolutionary trajectories of recovering lineages. Temperature fluctuations, altered precipitation patterns, and changing atmospheric composition provided a constantly shifting environmental backdrop for evolution and adaptation. The development of new climate feedback mechanisms involved complex interactions between recovering ecosystems and atmospheric chemistry. As plant communities re-established themselves, they began to influence local and regional climate patterns through their effects on water cycles, albedo, and gas exchange with the atmosphere. These vegetation-climate feedbacks operated differently in different regions, creating a mosaic of environmental conditions that promoted evolutionary divergence among recovering populations. Geographic isolation combined with environmental differentiation to accelerate speciation rates during the recovery period. The fossil record from the Middle Paleocene, roughly 5 million years after the extinction, shows ecosystems that were fundamentally different from both pre-extinction communities and modern ecosystems. These transitional communities represent unique experiments in ecological organization that have no modern analogues. The body size evolution of mammals during this period reveals the step-by-step process by which these small survivors grew to fill the ecological roles left vacant by dinosaurs. The increase in maximum body size was gradual at first, then accelerated as ecosystems stabilized and could support larger herbivores and their predators. Brain evolution among surviving vertebrates shows particularly interesting patterns during the recovery period. Many lineages developed enhanced cognitive abilities that may have provided advantages in navigating the unstable and unpredictable environments that characterize the post-extinction world. Sensory system evolution also accelerated during recovery as animals adapted to changed environmental conditions. Enhanced hearing, vision, and chemical detection abilities provided advantages for finding food, avoiding predators, and locating mates in ecosystems where traditional cues were no longer reliable. Behavioral flexibility became increasingly important as environmental conditions continued to change throughout the recovery period. Animals that could modify their activity patterns, feeding strategies, and social behaviors had significant advantages over those with more rigid behavioral programs. The development of new social structures among recovering animal populations reflects the changed demographic conditions that followed the extinction. With greatly reduced population sizes and altered resource distributions, many species evolved new forms of cooperation and social organization that enhanced their survival prospects. Reproductive strategies also evolved rapidly during the recovery period. Many species developed higher reproductive rates, earlier maturation, or more flexible mating systems as adaptations to the demographic challenges of post-extinction environments. The geographic patterns of speciation during recovery reveal the importance of landscape heterogeneity in promoting evolutionary divergence regions, with diverse topography and environmental conditions supported higher rates of speciation than more uniform landscapes. Island biogeography played an increasingly important role as sea level fluctuations during the climatically unstable recovery period created temporary land connections and isolated populations on newly formed islands. These geographic changes provided opportunities for allopatric speciation that contributed to the overall increase in biodiversity. The recovery of marine biodiversity followed different patterns in different ocean basins, influenced by factors such as water depth, current patterns, and proximity to continental margins. Shallow tropical seas recovered more quickly than deep ocean environments, but even the fastest recovering marine ecosystems required millions of years to approach pre-extinction diversity levels. The establishment of new biogeographic provinces during the recovery period created the foundation for modern patterns of species distribution. Many of the regional differences in flora and fauna that characterize different parts of the world today can be traced back to the geographic patterns of survival and recovery following the extinction event. Migration corridors and barriers that developed during the recovery period influenced evolutionary patterns for millions of years afterward. Mountain ranges uplifted during the post-extinction period created barriers to gene flow that promoted speciation, while river systems and coastal plains provided corridors for species dispersal and genetic exchange. The fossil record of the late Paleocene, roughly 10 million years after the extinction, shows ecosystems that had achieved new forms of stability but remained very different from pre-extinction communities. These mature recovery ecosystems represent successful experiments in biological organization under the environmental conditions that followed the catastrophe. Energy flow patterns in these recovery ecosystems differed substantially from both Cretaceous ecosystems and modern communities. The absence of very large herbivores and predators created food webs with different structural properties and energy transfer efficiencies. Nutrient cycling patterns also evolved during the recovery period as new combinations of species developed different approaches to resource acquisition and waste processing. These biogeochemical innovations influenced ecosystem productivity and stability in ways that continue to affect modern ecological processes. The legacy of that catastrophic spring day extends into every aspect of modern ecology and evolution. The selective pressures imposed by the extinction event influence the genetic architecture of surviving lineages in ways that continue to affect their evolutionary potential. Today, modern DNA analysis reveals that many gene families, important for stress tolerance and environmental adaptation, show evidence of positive selection during the early Paleocene period. These genetic signatures reflect the intense selective pressures that shape survival during the extinction and recovery. Comparative genomic studies suggest that the mutation rates and recombination frequencies that characterize modern species were influenced by the genetic bottlenecks and population expansions that occurred during the post-extinction recovery. The genetic diversity patterns we observe today still bear the imprint of that ancient catastrophe. The study of molecular evolution during the recovery period has revealed that many of the biochemical innovations that characterize modern life evolved as adaptations to the changed environmental conditions following the extinction. Metabolic pathways, detoxification systems, and cellular repair mechanisms all show evidence of rapid evolution during this critical period. Understanding the mechanisms of survival and recovery from this ancient catastrophe provides crucial insights for predicting how modern ecosystems might respond to rapid environmental change. The patterns revealed by studying the end, Cretaceous extinction offer both warnings about the vulnerability of complex systems and hope about life's capacity for resilience and renewal. The day the dinosaurs vanished was not simply a moment of ending, but a catalyst for biological innovation that continues to influence the evolution of life on our planet. That spring morning 66 million years ago set in motion processes of adaptation, diversification, and ecosystem reorganization that created the foundation for everything we see in the natural world today. As we face our own era of rapid environmental change, the lessons learned from that ancient catastrophe become increasingly relevant. The mechanisms of survival and recovery revealed by decades of scientific investigation provide a roadmap for understanding how life persists through times of crisis and how new possibilities emerge from seemingly impossible circumstances. The ongoing research into this pivotal moment in Earth's history continues to reveal new insights about the fundamental processes that govern life's response to catastrophic change. Each discovery adds another piece to our understanding of how resilience emerges from devastation and how the future grows from the ashes of the past. The story of that catastrophic day reminds us that we are all part of an unbroken chain of survival that stretches back through deep time to that spring morning when the world changed forever. Every living thing on Earth today carries within its lineage the genetic legacy of organisms that endured the most challenging conditions in our planet's history. In understanding that legacy, we gain not only knowledge about our origins, but wisdom about our future. The day the dinosaurs vanished teaches us that while catastrophe can end one chapter of life's story, it also writes the opening lines of the next. That ancient spring morning was simultaneously an ending and a beginning, a moment when destruction became the foundation for creation, and when the future of life on Earth was forged in the crucible of the most extraordinary day in our planet's long history. The implications of this ancient catastrophe extend into realms that most of us never consider when we think about extinction events. The molecular machinery of life itself was fundamentally altered by the environmental pressures that followed that spring morning. DNA repair mechanisms, cellular stress responses, and metabolic flexibility all underwent rapid evolutionary refinement in the surviving lineages, creating the biochemical foundation for modern life's remarkable adaptability. Recent advances in paleogenomics have revealed that the genetic bottlenecks created by the extinction event left permanent signatures in the genomes of surviving species. Population genetics models suggest that many mammalian lineages passed through periods where their entire species was represented by fewer than a few thousand individuals. This severe reduction in genetic diversity created founder effects that still influence the evolutionary potential of their descendants today. The surviving bird lineages show particularly fascinating genetic patterns from this period. Molecular clock studies indicate that the major avian orders that dominate modern skies underwent rapid evolutionary divergence during the first few million years after the extinction. This adaptive radiation was so swift and comprehensive that it represents one of the most dramatic examples of evolutionary innovation in the vertebrate fossil record. Interestingly, the genetic analysis of these ancient radiations reveals that surviving species possessed what researchers now term evolutionary flexibility genes. sequences that code for proteins involved in developmental plasticity and environmental response. These genetic tools allowed rapid morphological and physiological adaptation to the dramatically altered world, explaining how relatively few surviving lineages could diversify so quickly into the myriad forms we see today. The biochemical innovations that emerged during recovery weren't limited to large animals. Microscopic organisms underwent their own remarkable evolutionary transformations during this period. Bacterial and archaeal communities developed new metabolic pathways that could process the unusual chemical compounds released by the impact and the massive organic matter decomposition that followed. Some of these microbial innovations had profound effects on global biogeochemical cycles. New forms of sulfur and nitrogen metabolism evolved in response to the altered atmospheric chemistry, creating feedback loops that gradually restored more normal chemical conditions to Earth's surface environments. These microscopic evolutionary experiments laid the groundwork for the stable biogeochemical cycles that support modern ecosystems. The fungal kingdom underwent particularly dramatic changes during the recovery period. With vast quantities of dead plant and animal matter available for decomposition, fungal communities exploded in diversity and abundance. New enzymatic capabilities evolved that allowed these organisms to break down complex organic molecules more efficiently, accelerating the recycling of nutrients back into recovering ecosystems. Many of the symbiotic relationships between fungi and plants that characterize modern forests evolved during this period of recovery. The mycorrhizal networks that today connect forest communities and facilitate nutrient sharing between plants represent evolutionary innovations that emerged as forests re-established themselves in the post-extinction world. Plant biochemistry also underwent fundamental changes during recovery. The collapse of established plant communities created opportunities for chemical innovation as species competed for resources and defended against new types of herbivores. Many of the secondary metabolites that plants use today for defense and signaling evolved during this period of ecological upheaval. The evolution of new photosynthetic strategies became crucial as atmospheric conditions fluctuated during recovery. Some plant lineages developed enhanced abilities to photosynthesize under low light conditions, while others evolved mechanisms to cope with the increased UV radiation that penetrated the damaged ozone layer. These physiological innovations provided competitive advantages that shaped plant community structure for millions of years. Seed chemistry and germination strategies also evolved rapidly during recovery. Plants developed seeds that could remain dormant for longer periods, waiting for favorable conditions to return. Others evolved rapid germination and growth strategies that allowed them to quickly colonize disturbed habitats before competitors could establish themselves. The pollination biology that emerged during recovery created some of the most intricate coevolutionary relationships in nature. As plant and insect communities reassembled themselves, new partnerships formed between flowering plants and their pollinators. Many of these relationships involved chemical communication systems that had never existed before, creating the complex networks of scent, color, and reward that characterize modern pollination ecology. Herbivore-plant relationships underwent equally dramatic evolution during the recovery period. Without the massive browsing pressure of large dinosaurs, plants could invest energy in growth strategies that had been impossible throughout the Mesozoic era. Some lineages developed defenses against the new types of herbivores that were evolving from surviving mammalian lineages. The chemical arms race between plants and their herbivores accelerated during this period, leading to the evolution of sophisticated toxin production systems in plants and corresponding detoxification abilities in animals. These evolutionary innovations created the complex biochemical interactions that define many modern ecological relationships. Predator-prey relationships also underwent fundamental restructuring as new types of carnivores evolved to exploit the expanding populations of surviving herbivores. The hunting strategies, sensory systems, and physiological adaptations that characterize modern predators largely evolved during this period of ecological experimentation. The social behaviors that emerged among recovering animal populations reflect the unique demographic conditions that followed the extinction. With small population sizes and patchy resource distributions, many species evolved cooperative behaviors that enhanced survival and reproductive success. These social innovations became the foundation for the complex behavioral systems we observe in many modern species. Communication systems evolved rapidly as animals adapted to the acoustic and chemical properties of recovering ecosystems. New types of vocalizations, scent marking, and visual displays emerged as species developed ways to locate mates and coordinate activities in environments where traditional signals were no longer effective. Territorial behaviors and resource defense strategies also underwent innovation during recovery. With resources distributed differently than in pre-extinction ecosystems, many species evolved new approaches to claiming and defending the resources they needed for survival and reproduction. The migration patterns that developed during recovery created some of the great animal movements that characterize our modern world. As seasonal climate patterns stabilized after millions of years of instability, many species evolved the ability to track resources across vast distances, creating the spectacular migrations we witness today. Navigation systems evolved in parallel with migration behaviors, as animals developed increasingly sophisticated abilities to orient themselves across long distances. The magnetic, celestial, and chemical navigation systems used by modern migrants largely evolved as adaptations to the geographic and environmental challenges of the post-extinction world. Hibernation and dormancy strategies also became more sophisticated during recovery as animals adapted to the climatic instability that persisted for millions of years after the impact. The physiological mechanisms that allow modern animals to survive extended periods of resource scarcity evolved as survival strategies during this challenging period. Parental care behaviors underwent significant evolution as species adapted to the demographic challenges of recovery environments. Extended parental care, cooperative breeding, and other reproductive strategies that enhance offspring survival became more common as populations struggled to maintain themselves in difficult conditions. The life history strategies that characterize modern species groups largely crystallized during the recovery period. Fast reproduction and early maturation evolved in some lineages as adaptations to unstable environments, while others developed slower reproductive strategies that provided advantages in more stable conditions as ecosystems matured. Immune system evolution accelerated dramatically during recovery as surviving species encountered new pathogens and environmental stressors. The sophisticated immune responses that characterize modern vertebrates evolved as adaptations to the disease pressures and environmental challenges of the post-extinction world. Aging and longevity patterns also evolved during this period as species balanced the competing demands of reproduction and survival in challenging environments. The diversity of aging strategies we observe across modern species reflects the different evolutionary solutions that emerged during the recovery period. Developmental biology underwent fundamental changes as species adapted to the variable environmental conditions that characterized recovery ecosystems. Many of the developmental plasticity mechanisms that allow modern organisms to adjust their growth and maturation in response to environmental cues evolved during this period. The sensory biology of recovering lineages shows remarkable innovation as species adapted to altered environmental conditions. Enhanced hearing, vision, and chemical detection abilities provided crucial advantages in environments where food was scarce and predation pressures were changing rapidly. Circadian rhythm systems also evolved during recovery as species adapted to the altered light regimes that persisted for years after the impact. The sophisticated biological clocks that regulate modern animal behavior evolved as adaptations to the environmental chaos that followed the extinction. Thermoregulation strategies underwent significant innovation as species coped with the temperature fluctuations that characterized the recovery period. Many of the physiological mechanisms that allow modern animals to maintain stable body temperatures evolved during this challenging time. Digestive system evolution accelerated as surviving species adapted to new food sources and changed nutritional landscapes. The dietary flexibility that characterizes many modern species evolved as survival strategies during the resource scarcity that followed the extinction. Water balance and kidney function also underwent evolutionary refinement as species adapted to altered precipitation patterns and water availability during recovery. These physiological innovations became crucial adaptations that continue to influence species distributions today. The respiratory adaptations that evolved during recovery reflect the atmospheric challenges that persisted for years after the impact. Enhanced oxygen extraction efficiency and tolerance for variable atmospheric conditions provided survival advantages that shaped the evolution of modern respiratory systems. Locomotory innovations emerged as species adapted to the changed physical environments of the post-extinction world. New forms of running, jumping, climbing, and swimming evolved as animals exploited the ecological opportunities that became available in recovering ecosystems. The integration of all these evolutionary innovations created the biological foundation for the modern world. Every aspect of contemporary life, from the biochemical processes that operate within cells to the complex ecological interactions that structure ecosystems, bears the influence of that ancient catastrophe and the remarkable recovery that followed. Understanding this evolutionary heritage provides crucial insights into the fundamental processes that govern life's response to environmental change. The mechanisms revealed by studying the end Cretaceous recovery offer both warnings about the consequences of rapid environmental disruption and hope about life's extraordinary capacity for adaptation and renewal. The day the dinosaurs vanished was not just an ending, but the beginning of an evolutionary experiment that continues to unfold today. That spring morning 66 million years ago set in motion the processes of innovation, adaptation, and diversification that created every living thing we see around us. As we face our own era of rapid environmental change, the lessons learned from that ancient recovery become increasingly relevant. The evolutionary flexibility that allowed life to recover from the most catastrophic day in Earth's history provides a template for understanding how organisms might respond to the environmental challenges of the modern world. The ongoing research into this pivotal moment continues to reveal new insights about the resilience of life and the creative potential of evolutionary processes when faced with seemingly impossible challenges. Each discovery adds to our understanding of how destruction becomes the foundation for creation and how the future emerges from the ashes of the past. The legacy of that catastrophic spring day lives on in every heartbeat, every breath, and every thought. We are all descendants of the survivors, inheritors of an evolutionary heritage forged in the crucible of the most extraordinary day in our planet's history. In understanding that heritage, we gain not only knowledge about our origins, but wisdom about our capacity to adapt, survive, and thrive in the face of any challenge the future might bring. That ancient morning teaches us that while worlds can end in a single day, new worlds can emerge from the ruins with patience, persistence, and the remarkable creativity of life itself. The day the dinosaurs vanished was simultaneously the darkest and brightest moment in Earth's biological history, a testament to both the fragility and the resilience of the living world we call home. The profound transformation that followed that catastrophic spring morning extends beyond what any single discipline can fully capture. As we piece together the final chapters of this extraordinary story, what emerges is a testament to the interconnected nature of all life on Earth and the remarkable ways in which catastrophe can become the catalyst for unprecedented innovation. The atmospheric recovery that unfolded over the millions of years following the impact reveals processes of planetary healing that operated on timescales almost beyond human comprehension. The sulfuric acid aerosols that had blocked sunlight for years gradually settled from the stratosphere, but their chemical legacy persisted in ways that continued to influence climate patterns for millennia. Ocean chemistry slowly rebalanced as the massive quantities of dissolved carbon dioxide were gradually absorbed by recovering marine ecosystems and locked away in new limestone deposits. The carbon cycle itself underwent fundamental reorganization during this recovery period. Without the massive carbon processing capacity of large dinosaur populations, terrestrial carbon storage patterns shifted dramatically. Dead plant material accumulated in unprecedented quantities in some regions, while other areas experienced rapid carbon turnover as new types of decomposer communities established themselves. Soil formation processes accelerated in many regions as the absence of large herbivores allowed organic matter to accumulate and transform into rich, fertile substrates. These new soil types supported plant communities with different nutritional requirements and growth patterns than had characterized Mesozoic terrestrial ecosystems. The chemical properties of these recovery soils influenced plant evolution for millions of years, creating selective pressures that shaped the biochemical capabilities of modern plant lineages. Watershed dynamics underwent complete restructuring as vegetation patterns changed across continental landscapes. Without the trampling effects of massive dinosaur herds, river systems began to develop new channel patterns and flooding regimes. These hydrological changes created different types of aquatic habitats that supported novel communities of freshwater organisms. The establishment of new forest canopy structures had cascading effects on local climate patterns through their influence on humidity, temperature regulation, and precipitation. Dense, multi-layered forests that had been impossible under dinosaur browsing pressure began to create their own microclimates, supporting specialized communities of epiphytes, understory plants, and canopy-dwelling animals. Light penetration patterns in these new forest types created opportunities for plant species that had been unable to compete effectively in the more open woodland structures that had characterized much of the Mesozoic era. Shade-adapted plants diversified rapidly, developing specialized photosynthetic strategies that allowed them to thrive in low-light environments. The acoustic properties of recovering ecosystems changed dramatically as new types of vegetation altered sound transmission patterns. Animal communication systems evolved in response to these changed acoustic environments, leading to innovations in vocalization, echolocation, and sound-based territorial behaviors that continue to characterize modern ecosystems. Pollination networks underwent continuous reorganization throughout the recovery period as both plants and their animal partners continued to diversify and specialize. The complexity of these networks increased gradually, creating the intricate webs of interdependence that characterize modern pollination ecology. Some of the most sophisticated plant-pollinator relationships we observe today can be traced back to partnerships that formed during the early phases of ecosystem recovery. Seed dispersal mechanisms evolved in parallel with pollination systems as recovering plant communities developed increasingly sophisticated strategies for colonizing new habitats. The evolution of fleshy fruits, specialized seed structures, and complex relationships with animal dispersers accelerated during this period, creating the diverse dispersal strategies that support modern plant community dynamics. Chemical communication between plants became increasingly sophisticated during recovery as species developed warning systems to alert neighboring plants to herbivore attacks or environmental stresses. These chemical signaling networks, which operate through both airborne compounds and underground fungal connections, represent some of the most complex information processing systems in the natural world. The evolution of plant defense compounds accelerated as recovering ecosystems developed new herbivore-plant relationships. Many of the toxic and deterrent compounds that characterize modern plant chemistry evolved during this period of intense co-evolutionary pressure between plants and their animal consumers. Herbivore digestive systems underwent corresponding evolution as mammalian lineages adapted to process the new types of plant materials that became available in recovering ecosystems. The sophisticated gut microbiomes that allow modern herbivores to extract nutrition from difficult plant materials evolved during this period of dietary experimentation. Predator hunting strategies diversified rapidly as mammalian carnivores explored the ecological roles left vacant by theropod dinosaurs. Pack hunting, ambush predation, and specialized killing techniques all underwent innovation during the recovery period, creating the diverse predatory strategies that characterize modern carnivore communities. Social organization among recovering mammal populations became increasingly complex, as group living provided advantages in environments where resources were patchy and predation pressures were changing rapidly. Many of the cooperative behaviors, dominance hierarchies, and communication systems that define modern mammalian societies evolved during this period of social experimentation. Territorial behaviors and resource defense strategies underwent continuous refinement as population densities increased and resource competition intensified during recovery. The sophisticated territorial systems that characterize many modern species evolved as adaptations to the changing competitive landscapes of recovering ecosystems. Migration patterns stabilized gradually as seasonal climate patterns became more predictable and resource distributions achieved new forms of regularity. The great migration routes that define modern animal movements largely established themselves during this period as species tracked seasonal resources across continental landscapes. Reproductive timing and breeding systems evolved to match the changing seasonal patterns that emerged during climate stabilization. Many species developed increasingly precise timing mechanisms that allowed them to synchronize reproduction with optimal environmental conditions, creating the seasonal breeding patterns we observe in modern ecosystems. Parental care strategies became more sophisticated as species adapted to the demographic challenges of building sustainable populations from small surviving groups. Extended care periods, teaching behaviors, and cooperative breeding systems evolved as strategies for maximizing offspring survival in challenging environments. Life history evolution accelerated as species balanced the competing demands of reproduction and survival in ecosystems that were still undergoing rapid change. The diversity of life history strategies that characterize modern species groups crystallized during this period of evolutionary experimentation. Immune system sophistication increased dramatically as recovering populations encountered new pathogens and environmental challenges. The complex immune responses that characterize modern vertebrates evolved as adaptations to the disease pressures and environmental stresses of the post-extinction world sensory system. Refinement continued throughout the recovery period as species adapted to the changing sensory environments created by new vegetation structures, altered acoustic properties, and different chemical signatures in recovering ecosystems. Many of the sophisticated sensory capabilities that define modern animal behavior evolved during this period. Cognitive abilities underwent significant enhancement in many lineages as behavioral flexibility became increasingly important for survival in rapidly changing environments. Problem-solving abilities, learning capacity, and behavioral innovation all showed accelerated evolution during the recovery period. Memory systems and information processing capabilities evolved to help animals navigate the complex and variable environments that characterized recovering ecosystems. The sophisticated behavioral repertoires that define many modern species reflect cognitive innovations that emerged during this period of environmental uncertainty. Communication complexity increased as social groups became larger and more structured during recovery. The elaborate communication systems that characterize many modern species evolved as adaptations to the social challenges of coordinating group activities in complex environments. Cultural transmission of behaviors became increasingly important as learned behaviors provided advantages in environments where traditional instinctive responses were no longer adequate. The capacity for social learning that characterizes many modern species evolved during this period of behavioral innovation. Tool use and environmental manipulation behaviors emerged in several lineages during recovery as species developed new ways to access resources and modify their environments. These behavioral innovations represent some of the earliest examples of the technological capabilities that would eventually characterize human evolution. Play behavior and exploratory activities became more sophisticated during recovery as extended juvenile periods allowed for increased learning and behavioral development. The complex play behaviors that characterize many modern species evolved as mechanisms for developing the behavioral flexibility needed to survive in variable environments. Aging patterns and longevity strategies diversified as species adapted to different environmental conditions and demographic pressures during recovery. The variety of aging strategies we observe across modern species reflects the different evolutionary solutions that emerged during this period of life. History experimentation, stress response systems became more sophisticated as species adapted to the environmental variability that characterized recovery ecosystems. The complex physiological mechanisms that allow modern animals to cope with environmental challenges evolved during this period of adaptive refinement. Circadian rhythm systems achieved new levels of precision as species adapted to the stabilizing light regimes that emerged as atmospheric conditions normalized. The sophisticated biological clocks that regulate modern animal behavior represent evolutionary innovations that emerged during this period of environmental transition. Metabolic flexibility increased in many lineages as species adapted to variable resource availability during ecosystem recovery. The diverse metabolic strategies that characterize modern species evolved as adaptations to the nutritional challenges of the post-extinction world. Thermoregulatory mechanisms became more sophisticated as species adapted to the climate variability that persisted throughout the recovery period. Many of the physiological mechanisms that allow modern animals to maintain stable body temperatures evolved during this challenging time. Water balance strategies diversified as species adapted to the altered precipitation patterns and water availability that characterized recovery environments. These physiological innovations became crucial adaptations that continue to influence species distributions and ecological relationships today. Respiratory efficiency underwent significant improvement as species adapted to the atmospheric changes that persisted for millions of years after the impact. Enhanced oxygen extraction capabilities and tolerance for atmospheric variability provided survival advantages that shaped the evolution of modern respiratory systems. Locomotory capabilities continued to diversify as species exploited new ecological opportunities in recovering ecosystems. Specialized forms of movement evolved as animals adapted to different habitat types and resource acquisition strategies, creating the diverse locomotory adaptations we observe in modern fauna. Digestive efficiency increased as species developed new capabilities for processing the plant materials and prey types that became available in recovery ecosystems. The sophisticated digestive systems that characterize modern herbivores and carnivores evolved during this period of dietary adaptation. Detoxification systems became more sophisticated as species encountered new environmental chemicals and dietary toxins in recovering ecosystems. The complex liver and kidney functions that allow modern animals to process environmental contaminants evolved during this period of chemical adaptation. The integration of all these evolutionary innovations created biological communities of unprecedented complexity and sophistication. The ecosystems that emerged from the recovery process were fundamentally different from anything that had existed before, representing new forms of biological organization that combined elements from surviving Mesozoic lineages with novel adaptations to post-impact conditions. These recovery ecosystems achieved levels of productivity and diversity that eventually exceeded those of pre-extinction communities, demonstrating life's remarkable capacity for creative response to catastrophic environmental change. The biological innovations that emerged during recovery created the foundation for the continued evolution of complexity and diversity that characterizes the modern world. And so we reach the end of our journey through the most extraordinary day in Earth's history. 66 million years after that spring morning, when a mountain-sized asteroid rewrote the rules of life on our planet, we can finally piece together the complete story of catastrophe, survival, and renewal that shaped everything we see around us today. What began as a single moment of cosmic violence became the catalyst for the most dramatic transformation in the history of life. The day the dinosaurs vanished wasn't just an ending. It was the opening chapter of our modern world. Every mammal that walks the earth, every bird that takes flight, every forest that grows carries within it the genetic legacy of those remarkable survivors who endured the most challenging conditions our planet has ever known. The story reminds us that life's greatest strength isn't its stability, but its capacity for change. In understanding how our ancestors survived the ultimate catastrophe, we gain wisdom about resilience, adaptation, and the extraordinary creativity that emerges when life faces its greatest challenges. Thanks for joining me on this incredible journey through deep time. If this story of survival and renewal resonated with you, hit that subscribe button and let me know in the comments what other mysteries of our planet's past you'd like to explore together. Until next time, keep looking up at the stars and down at the rocks, because both tell the same amazing story of where we came from and where we might be going.